Hi. As discussed during the last lecture I made, I plan to do a live presentation that's a tutorial on Python, and today I'm going to be using the Jupyter Python editor, IDE. Just as a brief introduction, I'm on a Windows system. I installed Anaconda for Windows. Depending on which operating system you're on, you'll have a different interface to get Python set up. So installing Python is not the topic of this video. I used Anaconda, which is a distribution of Python that is easy to manage. One of the things that it lets you do is use a Python virtual environment, which I always use. So this is the Anaconda Navigator in Windows. And from within the Anaconda Navigator, when it loads up, it displays several applications that you can use. I have clicked on Jupyter Lab and I hit launch. So Jupyter Lab is the IDE that I'm demonstrating today. Also, at the top in this drop down, there are a variety of different Python environments I can use. I can have multiple different versions of Python on the same machine, and I can switch back and forth between them. Again, I'm not going to talk about how you do that in the video, but right now I set up a version using Python 3.8 for this course. All right. So again, if you like, I can do another video where we walk through setting up Anaconda and setting up this environment. I clicked launch on Jupyter Lab, and when I did that, it popped up with a browser window set to the URL localhost, that's my machine, at port 8888 using the lab interface. This is a web-based integrated development environment, or IDE. On the left-hand side, I have a folder where I can look at different files on my system. If I hit the plus sign, I get this start screen. Yours might begin with the start screen if you haven't already opened something. At the top, I can launch something called a new Jupyter Notebook, which is what I'm going to be demonstrating today. Also, I can create a new Python console. If I click on this button, a tab like this one down here will appear. I can, of course, take these tabs and move them wherever I like them, but I like my console right where it is. In addition, I can open a terminal. If I click on this window, it'll create a terminal on my computer like this one. I'm on a Windows computer, and so the default terminal that it opens is Windows PowerShell. I've installed Bash on my system. I will generally demonstrate things using the Born Again shell, or Bash. I just typed in the word Bash, and with the current color scheme, you couldn't see it because it was yellow on the PowerShell. But now that I'm in Bash, you can hopefully see the text a little bit better. Maybe I'll zoom in a little bit. All right. So this is a command prompt that's Linux style. It's Bash. I can type ls to list all the files. Right. There are different themes that you can use in Jupyter. I thought that the light theme would look better, but the dark theme is generally more comfortable. So maybe we'll stick with the dark theme for the rest of this discussion. Okay. So these are some of the different things that you can do with Jupyter and with the launcher. Also, you can edit documentation using a markdown file, or you can open contextual help. If you click on this button, this tab will show up, and you'll see me use this tab to display help on the different functions in Python. So that's sort of the brief introduction. One other thing is if you hit Settings and enable the extension manager in Jupyter, then you get this little puzzle piece, and you can turn on different features. The reason I bring this up is because I've enabled the table of contents feature, and you'll see me use that as I present the material. Now, on to the lesson. In the center of my screen, you see what is called a Jupyter Notebook. It looks like a document with styled text. I've titled it A Brief Introduction to Python in Jupyter. I plan to share this with you. I have not shared it with you yet. So for now, just watch. If you're not watching this live, you can go and download it. I'll put it up on a Git repo or a Git repository. I'm pausing for a second so I can pull up the chat in case anybody shows up. All right. So again, I haven't made this one live. I will make it live. What I've done is I've presented a little bit of information on Jupyter. So this is, if you see when I click on the left-hand side, there's a yellow bar that shows up. That's because each one of these is a cell. So it's its own little unit of the document. If I double-click on a cell, I can edit the contents. The cells are typeset using Markdown, which is a very simple language, much simpler than HTML for writing documents. A line which begins with a single hash sign is going to be a top-level heading. A line that begins with 2 hash signs would be a second-level heading. A line that begins with a minus sign followed by a space is a bullet point. If you want to insert HTML, you can use HTML tags. KBD is the HTML tag that makes things look like their keyboard shortcuts. Notice that the A is in italics and the B is in italics. If you want to make something in italics, you can either surround it by underscores or by an asterisk. If you use 2 asterisks, it becomes bold text. So 1 asterisk for italics, 2 asterisks for bold, and you can really quickly create some slick-looking documents. Another thing about Markdown, I'll just demonstrate it right here, is if you do 3 ticks, then it does code. You see that it's trying to syntax highlight it as if it's Python. I'm sorry, I have to hit Escape and M to convert the cell to Markdown, as indicated right there. And then when I hit Shift and Enter, it'll render that cell out. So this is in a fixed width font as if it's code. If you want to make it look like it's code in a particular language, like Python, so this would be a Python definition of a function that does nothing. If I want it to get rendered with the correct syntax highlighting, I can put the language right afterwards. And if the tool has a lexer for that language, it'll start to render each token type in a different color. So the keywords now are rendered properly. If I don't do Python, that goes away. If I do, then it's rendered like Python code. So you can actually do this to document code pretty well. If I hit, there's ways that you can cause it to number the cells, but the easiest thing is, well, I'll leave it at this. Okay, so that is Markdown. You can put code and style the text. So this is going to be the environment that I'm going to use to demonstrate Python. Again, I have a Python interactive shell here in which I can type Python statements, and if I hit Shift Enter, they're immediately executed and I see the result. And then over here, similar to that, it's like a Word document. It's just that inside each one of these cells, I have a combination of either Markdown cells or executable Python shells. So to begin with, Python is a very high-level scripted language. By very high level, I mean this is sort of a term that's used for a lot of the different scripting languages. Low level, generally, it's simpler to implement, harder to use as a rule. And then as you get higher level, it becomes easier for humans to use, but more complicated to implement the compiler and the runtime environment necessary to use it. So Python falls under that very high-level language. It's completely scripted. Not a lot of baggage on humans, or at least it's not intended to. There are several different potential interpreters for Python. If I come here to the terminal and clear it, I can just type in the word Python, and it'll bring up a Python shell if I had installed Python. Right now, I'm actually not in my Conda environment, so and I don't want to deal with that for now. But you can run a Python interpreter from there. But the default Python interpreter is pretty lacking in features. There is an another interpreter that people generally use called IPython. So let me just do a new terminal real quick. A new terminal. And here, conda activate CSE465. That was my environment. So now I should be able to type in Python. And this is the default Python shell. I'm not quite sure how well you can see this. I'll probably, if I edit the video, zoom in on it. But the left-hand side is 3 greater than signs. And if I type in 3 plus 3 and hit enter, it'll show the result as 6. If I type the word print and I say hello world, this is the way that you write your hello world function in Python. It's that easy. However, it doesn't have, like if I hit PR and I try to get help by pressing tab or control space or anything like that, it doesn't have any of those features. In order to exit the shell, I type in the exit function. So it's missing some features to provide dynamic help and autocomplete. Over here, what we have is, in this terminal, this is representing the IPython shell. You can launch it from a command line just by typing IPython instead of Python if it's installed. And you'll notice that the prompt looks a little bit different. It's colorful now instead of being all black and white. So immediately that makes it a little bit more friendly. And if I type in PR and I hit tab, it does autocomplete suggestions for me of what I might intend to say. I'm going to be biased here and say that real programmers don't spell the whole word. Real programmers type in PR tab, right? As it becomes a source of efficiency, and also it makes sure that you spell the word correctly. And often you don't remember what everything's called, so you can actually use tab and then cycle through the different options to help you remember what's available to you. Okay? So this would be the IPython shell. And to exit it, you can call the exit function, but you can just also type exit by itself from the IPython shell. What's displayed in the lower right-hand corner is an IPython shell, but it's managed by Jupyter, which is why the prompts look even a little bit more simplified. Okay. So coming back to the notebook, I'm going to collapse this away. And so this is the IPython shell. In addition to being able to use IPython from your terminal, which is what I would recommend over Python, so you can use IPython from your terminal, there's also a resource that became available recently, maybe like a year ago, from Google called Colab, and you can go and log on to colab.research.google.com, and they'll be hosting a Jupyter notebook, but they've changed the keyboard shortcuts a little bit. So from there, you can actually use a GPU if you want to do any machine learning stuff. It's another thing to explore. And then finally, you've seen me in another video potentially use an IDE. Some different IDEs you might use are Spider, which comes with Anaconda, but it doesn't seem to work very well on Windows, I found, with Python 3.8. Or PyCharm. PyCharm is a top-notch IDE. I use it all the time. It's free for you if you're a student. You can also use Eclipse. I don't tend to use Eclipse, but it's supposed to be very good. So with that kind of background, so hopefully you've set it up. I've introduced the tools and the environments a little bit. Then we can begin to talk about the basics of Python. So again, this is a Jupyter notebook. If I hit Shift Enter, it executes and moves me to the next cell, and I'm going to use that to navigate down through it. The first thing that you're going to want to do is check which version of Python that you're using, because the things that I'm going to present to you are from Python 3.8. I'm following the same outline as the Python tutorial for Python 3.8. So it'll be along those lines. How can you tell which version of Python you're using? The code that I've just selected here says Python 3.8.2. So that's one way that I know. The other thing is, now I'm going to click on table of contents here. So there we go. In order to check your Python version, you can import the sys package. So in Python, you have packages and modules. They both pretty much look the same. A package is just a collection of modules in a folder. And then each package or module will have within it different variables and functions and classes that you can use, types that you can use. So in order to check the Python version, I import the sys module and I print sys.version, and it also displays that same message that this is Python 3.8.2. Right? So moving along, we're going to do sort of an informal introduction to Python. All right, so I'm using this these table of contents here, and so the following outline, as I say, is from the Python tutorial. It's, if I click on it, it'll open up in a new tab. This is provided by from the Python website for Python 3. This is their introduction, in which they provide a bunch of examples and documentation. So for more details about anything that I demonstrate, you can come and look at the Python tutorial. In order to use their website, on the right-hand side, there's a button for each one of these little code cells that hides the output and hides the prompt. And this becomes something you can copy and paste into a notebook. And that's what I've done here in order to create most of these cells. I've also added a little bit of my own flavor, or my own additions to them. So just a raw beginning to Python. In Python, the hash tag symbol is a comment. So hash, this is the first comment. We see it rendered in a different color. And hash, this is a second comment. It goes to the end of the line. There are not Python commands. There are no Python commands to do a block comment. Some people will put comments in strings, and that's not really the correct thing to do. Right? So if you want to select multiple lines of text and comment them all out, most editors will let you do comments using a keyboard combination like I'm doing right here. I'm pressing the control key and the slash key at the same time, and it comments out the block. So there's no need for block comments in Python. You will find that some of the features of Python rely on you having a good text editor. So here we have, I'm assigning a variable, a value to a variable, and then here we see some text. And one thing about the comment character in Python is if it occurs in a string, then it is not a comment character. Right? So that's sort of, pretty much anywhere else it occurs, it comments out the rest of the line, unless it's after a quotation mark, in which case it's part of that string. Right? So there's that. So here we've done that. We've created a variable called spam, and we've created some text. You'll notice up here that the text automatically, or the contextual help automatically updated itself when I put my cursor over top of something. The data type of text right now is a string, and I'm getting help on string type. The data type of spam is an integer, and I'm getting help on the integer type. So that's a very handy feature. So if you want to display a value in the Jupyter notebook, then you just type the value. The value of the last expression in a cell gets displayed as the output below the cell, with the number corresponding to it. This is actually stored in a variable in Python, which I can access later if I want to. If I want to display the text, I just put text by itself in a cell, and it'll display a representation of that value. Same thing works here. If I type an expression of any type and I hit Shift-Enter, it'll display the result of that expression. If it's a mathematical expression, it displays the result of that mathematical expression. So of course, moving into using Python as a calculator, we can discuss some things. First of all, numbers behave as you'd expect. You have addition. You can write complicated expressions involving multiplication and addition. Something that may be different than a language that you're used to is that division does not truncate in Python 3. So if I were to take 9 divided by 5, it's 1.8. Most of you are used to Java, which would try to keep the data type of the result to be the same type as the data type of the operands. If you'd like to keep the result an integer, you can use the truncating division, which is 2 slashes next to each other. If you use a negative 9/5, again, it is going to round down. So not -1, it's not clipping off the decimals, it's rounding down, so it's a -2, right? If I were to do this as a floating point number, I get a -1.8. The least integer below it is a -2. Another function that's built into Python that's pretty useful is to round to the nearest integer, which works exactly as you'd expect. And if you want to do additional operations, oh, and by the way, you can round to whatever number of digits that you want. So if I want to round that to 2 digits, it takes a second optional argument, which is the number of digits you'd like to round to. The math module contains a number of additional math functions you might like to use. The syntax here, in order to import everything from a module, is you use the word from. We'll talk about modules a bit more later. The module name, and then you import star to import everything from it, which means that every function that was defined inside the math module, I now have access to it without needing to say math.floor or anything like that. So the floor of 9/5 is -2. The ceiling of -9/5 is 1. So that's the floor and the ceiling operation. If I do integer division, 17/3, I get a 5, and I give a remainder of 2. Right? So this is not from the math module. This is standard Python. The modulo operator is the integer remainder. It'll actually be the floating point remainder as well. 17 mod 3.1 is 1.4999. So the multiple of 3.1, which gets me just below 17, is 1.4999 away. So it's it works for floating points and integers. Again, of course, 5 times 3 plus 2 is 17. That's what the modulo does. In Python, if you want to raise a number to a power, there's a double asterisk operator. So if I wanted to compute 5 squared, it would be 5 double asterisk 2. If I want to calculate 2 to the 7, it would be 2 double asterisk 7. And in terms of order of operations, if I were to say 5 double asterisk 2 times 2, it could be 25 times 2, which is 50, or it could be 5 to the 4th, which is something completely different, and I don't want to do it in my head. So this is 50, whereas if it had done the other order of operations like that, I would have gotten a 625. So the order of operations is going to be that the double asterisks is higher than most of the other things that you see. Of course, in Python, you can store values in variables. In Python, you do not need to declare the type of a value. You do not need to declare a data type for each variable name. The variable width will be assigned to an integer, and then it becomes an integer variable. The variable height will be assigned to another integer, and it becomes an integer variable, and it'll stay that until I assign something else to it. So I can use width equals 20, and then I can say height is 45, and I can multiply the two out. Right? So that works, that's handy. If I try to read from a variable that doesn't exist, I will get an error, as one probably hopes. And I can construct kind of complicated expressions using not only integers, but the floating point numbers as well. So here we're trying to calculate some syntax. That shouldn't be surprising to you. Now, as I said, the thing that gets displayed is the result of the last expression in the cell. If you want to hide even that, then you put a semicolon at the end. So a semicolon is not required at the end of lines in Python. It only really has meaning in an interactive shell to suppress the output of the last line. Each time I compute a value, the result of the last expression is stored at the underscore character. So over here, if I were to type in underscore and hit enter or shift enter, it's a 6 because that was the result of the last expression. So over here, I've calculated price times tax, and if I add it back into price, I get 113. So the result of the previous cell is here in the underscore. Now I can take this variable value here, which was the previous thing I computed, and round it to 2 decimal places. So you can chain operations together like that. Not shown here, every single cell in a Jupyter notebook has its own variable. So looking at the left here at cell 30, I know that that result is in the variable underscore 30. So Jupyter notebooks hang on to all of their outputs unless you clear them, unless you delete them, right? So remember that they're all being kept, not just displayed. So it is true that the order of execution in Jupyter matters. If I go back here and I try to hit round, it's not going to say 113 anymore, it's going to say 12.56. That can get very confusing when you execute the cells of a Jupyter notebook out of order. So you need to pay attention to the number on the left-hand side to tell you that this was executed before this one. It is nice to be able to execute cells out of order sometimes. In many cases, the Jupyter notebook itself is the user interface that you want for some task. You declare the variables, you set them in the cells, and then you do computation based on them. And you describe how to use them in the markdown cells. So moving on, we've seen integers and floating point types in Python. There are also strings in Python. You can use a variety of different ways to quote a string. For instance, single quotes is the default and the preferred stylistic way to write a string. So this is the string spam and eggs. If you want to use a single quote within your string, you can escape it using the backslash character. So here we're using a single quote as an apostrophe. You just put a backslash in front of it and you can get the string doesn't. You'll notice that because it included a backslash, by default, Python rendered the string using double instead of single quotes. And Python actually has at least 4 different ways that you can quote a string. And you can choose a different one based off of what expresses the string most clearly. For instance, if I want to use a single quote in my string, then I can use double quotes to quote the string. Conversely, if I wanted to use a double quote in the string, I can use single quotes on the outside. So being able to switch between single and double quotes means that you don't have to escape characters as much, and it makes your text more readable. So here I can use a single quoted string in order to use double quotes inside the string. Alternatively, I could have used double quotes on the outside and then escaped the double quotes on the inside. I would have gotten the same results. I don't know why I've got this twice. So the other thing that I wanted to point out is that if you put 2 strings, this only works for string literals, meaning that no variables, right? So if you put 2 string literals next to each other, they're automatically lumped together as one string. And this is useful when you have a long string that you can't fit all on one line. You can put a pair of parentheses around it, and then you can break it up into parts that wrap from multiple lines. Because in Python, indentation is necessary for certain structures, which means that if your code indents too far, then it doesn't all fit in one screen width. So managing the screen width becomes an issue sometimes. That being said, if you do manage the screen width, it's very readable. So each one of those outputs that was produced, even though it was a string, you'll notice that they always had quotes around them. If you'd like to display content to the user, then you use print, right? And that will display the string as it's intended to be seen, without escape characters and without quotes, right? So in this case, we are printing the string C:\some name. The problem is the backslash, which is used in paths in operating systems like Windows, is also used as the escape character by convention in strings in many languages. In this case, \n is the shortcut for a new line, and so this, when we went to display the string using print, it was broken up into 2 lines. In order to avoid that, you have to escape backslashes in your string, right? So now, every time I wanted a backslash, I used a double backslash, and it works. Now, although it does work, that can be very difficult to read, especially when you're using something like a regular expression, which itself needs escaped backslashes, and before long, you're typing 4 or more backslashes in a row. To help you deal with that, Python has a raw string. If you put the letter R before, and it doesn't matter what kind of quote you use, but if you put the letter R in front of the first quote, then it won't do string escapes inside the string anymore, in which case all of those backslashes are interpreted as exactly that, as backslashes, right? And this becomes a new string literal. If you wanted to break it up into multiple string literals, each one of those chunks would need the R in front. If you leave the R out of any of them, then it's not interpreted as, that chunk of a string is not interpreted as a raw. So in addition to raw strings, you also have triple quoted strings. And the idea of using a triple quote in Python, and it could be a triple double quote or a triple single quote, it doesn't matter. The idea of a triple quote in Python is that you do not have to type in new lines. So it'll actually, the string continues to be considered part of the string until it finds another triple quotes, including all of the new lines. So if I try to print this string, it gets the whole thing, including the line breaks here and here. Any line that ends in a backslash, if it's the last character of the line, then that's a line, that means that it just wraps around to the next line with no new line. So a line in anything in Python, if you want to overflow the line, you can use a backslash as the last character. That's why this thing doesn't begin in a new line. So you can use that, for instance, to print help messages. Okay. Some other things about strings. You can multiply strings, which will repeat them. So multiplication is repetition for strings, and you can add strings which will concatenate them. So for instance, 3 times un plus is un. It gets repeated 3 times and then concatenated with the word ium. Python has overloaded the plus operator for this. I already showed it to you out of order, but if you concatenate, if you put 2 strings next to each other, they get concatenated. It doesn't matter if you put an R in front of one or both. There you go. I put an R in front of that one so that I could put a slash in it if I wanted to, and that works just fine. You'll notice that Python inserted the escape characters for me because I used a raw string. So just remember that raw strings can be useful. Okay. You can, of course, store a string into a variable. Notice that I did not declare any type for that variable. Python uses something called duck typing, which means that that variable is a string type if it looks like it's a string type, right? So this is part of the idea of this very high-level language. You're sacrificing a little bit of the robustness that you get from static analysis to do type checking. But in sacrificing that, it becomes much easier to write things down because you don't have to think as much about it while you're producing the code. So it's a simpler language to use. Now, one thing to point out is this string concatenation works only for literals. If I tried to concatenate A and B together like this, I would get an error. You can't put a variable next to a string, even if that variable is holding a string. But it works just fine for literals, right? Again, if you want to put several strings together and you want to break them apart, then you can use parentheses. Okay. I show you the same thing multiple times in a row, deal with it. So here, again, prefix is stored in a variable. If you want to concatenate them by putting them next to each other, it doesn't work, but you can use the plus sign, and the plus sign does string concatenation even with variables, right? So if in doubt, use the plus sign. Here we're creating a word called Python. Now Python, this variable's type is a string right now, which means that it supports all of the operations that a string does, including accessing individual characters using the indexing operator, or square bracket. So word 0 is going to be the character at position 0, which is a P. Word 5 would be the character at position 5, which is the N. That's the 6th character, by the way. In addition to indexing from left to right, you can index from right to left. The rightmost character is at index -1. Then you continue to move from right to left. Notice that the rightmost character is not at -0 because -0 and 0 are the same. So you can access them forward with positive indexes from 0 to the length -1, and with negative indexes from 1 to the length, -1 to negative the length. In addition to accessing individual characters, both from left to right or right to left, you can also use slicing. So if I want to extract the substring that begins at character 0 and it ends just before character 2, so this will be characters 0 and 1, then I could use word 0 colon 2. It gives me word 0, letter 0 and 1, pi. If I want to get from 2 up to 5, so 2, 3, and 4, I can do word 2 colon 5. Notice it didn't have the N, which is the 5th character. If I don't want to type in the 0, so basically if you leave the beginning index out, right? So it's the beginning index colon the end index. If you leave the beginning index out, it'll start from the beginning of the string, wherever that is. If you leave the ending index out, it'll go all the way to the end of the string, wherever that is. So that's from 2 to the end, and the other part was from 0 to 2. In essence, I've just split it into 2 parts, right? If I, of course, concatenate those two together, I get the original string back. If I want to get the first 4 characters, 0, 1, 2, and 3 are the indices that I just plucked out of the string, and the remaining. Okay, so from 4 onward, O and N. Just to help you remember, here, I'll go ahead and execute that. Going from left to right, you've got 0, 1, 2, 3, 4, 5 are the indices of each one of these squares. 6, if you tried to access it, would be in out of range. You'd get an exception. There's nothing out here. Moving backwards, -1 is the same as 5. -2 is the same as 4, and so on. -5 would be the same as 1, and -6 is the same as 0 in this string. If I try to access beyond the end of the string, I will get an out of range exception, right? So Python will use an exception to report most errors. However, if I try to slice beyond the range, it'll just stop at the end, right? So slicing, you're allowed to go past the end of the string in the slice as long as it overlaps, right? Here again, I just get the empty string. So go back and delete where I said as long as it overlaps, right? You can slice beyond the range of the strings and it just gives you empty strings. You can not assign to string variables. Strings in Python are read-only objects. There are some languages where they are not read-only, although conceptually they are intended to be treated that way if you use a string. That's part of the semantic idea of what separates a string from an array of characters. So while some languages will have mutable strings, that is probably going to be stylistically a bad thing to do if you wanted to change them. If I wanted to construct a word which was like Python but began with a J, I can append the last part of the word to the letter J, and then I get the string Jython. In order to get the length of a string, you use the len function, len. Python is, again, while it seems new, it is actually older than all of you. You know, len has been around from the beginning. There's no reason to type the GTH. I mean, just 3 extra letters. So some useful methods that I've inserted into this notebook. These come from Python 3.7. They were added to the language, which is within a few years, like a year or two of now. It's formatted strings. So in C#, for instance, this is what the $$ symbol would do, right? So here we have the F, and what's going to happen is inside of the curly brace, I can type regular Python expressions, and these get evaluated and replaced with the string representation of their value. So it'll put a 6 there because it'll evaluate 3 plus 3 and get a 6. Right? So that becomes a convenient way to format things exactly the way that you want. Let me show you a little bit more about the formatting. Here I've created a variable x. X is now an integer, 5. And in Python 3.8, if you type in the variable's name with an equal sign after it, it'll print the words x equal and then the value of that variable. In addition, you can put a colon anywhere. Here I could have put a colon as well. Colon 05, and that would do 5 decimal places with leading zeros, right? So after the colon, you can do format specifiers. It's worth getting to know how to do these. So in this case, I've done a colon, and then the greater than sign means just shift it to the right with no leading character. You have to look on Google to find out what these format specifiers are. I'll leave that to you. And use 10 places. So that's useful to line things up in your output. The idea here is because I said x equals, it doesn't just print the value of x, it puts an x equals in it as well. So here, if I didn't put the equals sign, it just prints the value of x, and in this case, I used leading zeros in order to display it. And again, the result is a string. I'm not printing this out, it's just that the result of the expression is a string. Some other operations that are very useful on strings, there's the split operation. The split operation, by default, it'll split the string around the white space and it'll give you a list of characters. So now instead of 1 string, I have 5 different characters. You can pass in some arguments to split. So again, the split function takes the first argument is the character that you want to split around, and then the second argument, if you give it, will be the number of splits to make. So in this case, it'll make 1 split around a space. And so I got the 1. In this string, I'm choosing to split it around the hyphen instead of a space. So you can actually, as you imagine, probably use this for some text processing stuff. Now, if you forget to put the function call operators, so notice that it's a function call that needs the parentheses. If you leave those out, then what you get is a closure. It is an object that is bound to that string. All right, so that's a difference. So just remember to call the function. Here, also, if I want to get help on the function, sometimes it doesn't show up in the documentation. if you put a question mark afterwards and hit Shift Enter, it should show you the help. In this case, it didn't know what that was, but if I were to type in str.split, then I get the documentation here and there as well. Right? So it didn't know that string literal. The Jupyter system wasn't intelligent enough to tell that this string literal was a string literal. But yeah, putting a question mark either at the beginning or the end of a line will bring up the documentation for that line of code. So here we've got the strip method, which will remove the white space from either side. Here we've got the L strip, which will only do it from the left side, and the R strip, which will only remove the white space from the right side. That's just another useful text processing function. As I said before, if you want to get help on the split function, in this case, it didn't know what the data type of this literal was, so it didn't give me any help. But if I say I want string.split or str.split, I can put the question mark afterwards or before, and it'll give me the help right here inside the notebook. And of course, this thing, even if I don't put the question mark, as soon as Jupyter knows what this is, it'll display the help in the help window. So that can be pretty useful. Again, if I hit tab or shift tab, then it will bring up help, and it might take a second. So tab, and it's the autocomplete. I either mean to type split or split lines, which will break it around the new line character. And then if I hit the left parentheses and I hit shift tab, I don't even need to hit the left parentheses. If I hit shift tab, it brings up the documentation. And if I keep hitting shift tab, it used to bring the help up, but okay. Here I can see that there's some additional arguments, and I'll explain what this slash means later. And you can see some default arguments over here with their default values specified. If I use 2 question marks, it'll dig up the source code if it has it, which it doesn't for this. So that's, yeah. Moving forward in Python, there is no real array type. In Python, a collection of values is stored in a list. Again, arrays are in some sense a lower level concept, and in order to use arrays in Python, you're going to have to use library code from either the Python array module, but more likely from a module called NumPy. In order to actually manipulate less collections of data using the standard library or the standard tools in Python, you're going to create a list. In order to create a list, you just put the values inside square brackets with commas separating them. So here, squares is assigned to a new list. When I go to display it, there's the list. You can index lists just like you would with the string. Squares 0 is the first item in the list, which is a string. Squares -1 is the last item of the list, which is the number 25. If I want to get the items at -1 and -2, so this will be the last 2 items out of that list, I can use slicing. Actually, this tricked me. Remember, it's -3, -2, and it goes all the way to the end of the string, so it'll get -1 as well, right? So this gets the last 3 items of the list. So -3 colon got me 9, 16, and 25. If I want to do a shallow copy of the list, what is a shallow copy? I realized today that talking to a junior that not everybody knows this, but suppose I had a list of lists. Remember, when you have objects that are references to things, if you copy the list, that list might be referring to the same object as some other list, right? So that's called a shallow copy. In a deep copy, I would duplicate the list, and then I'd go through every element of the list and I would duplicate those as well, and I would recursively do that. And so there was no overlap between my copy of the list and the original one. If you just put a colon inside square brackets, that creates a shallow copy. And in fact, I believe that 3 dots in a row, the tilde operator will also create well, ellipses are their own operator, their own symbol, the 3 dots in Python. And when you're using a library like NumPy, like I said, that uses arrays, sometimes those will also mean to make a shallow copy. Apparently, it doesn't work for the Python lists. You can concatenate lists using the plus operator, so it works just like strings would. You can, unlike strings, you can modify lists. So suppose we tried to create an array of cubes, and then we realized that there's a problem because cubes 3 should be, so we've got, it should be the cube of a number, right? But cubes of 3 is 65, and 65 is not anything cubed, right? So we've got 1 cubed, 2 cubed, 3 cubed. This should be 4 cubed. What is 4 cubed? It is 64, not 65. So we can modify it. Remember, we're using the exponent operator in Python. So we can modify cubes 3. We can actually write out 64 to it and then display it. So lists in Python are mutable and strings are not mutable. Cubes, if we want to add to the string, we can call cubes.append. It does not create a copy of the cubes, it actually modifies that list's representation in memory. I can continue to add numbers cubed to it using the append operator. That'll add one item at a time versus the plus operator in which you can add a whole list of things, right? Here we have a list of letters. You can use slicing just like with strings, but the slices themselves are mutable, right? So this is letters 0, 1, and we're going to do 2, 3, 4, but not 5, right? So these 3, we're going to replace it by those uppercase letters. So if you write to a slice, it works just fine. It'll copy the contents of the right-hand side into the slice on the left-hand side. And in fact, if the slice on the right-hand side is a different size than the slice on the left-hand side, then you can actually cause your list to shrink or grow. For example, if I take the entire list of letters and I assign the empty list to that slice, I've removed every item from the list of letters. Now, if I rebuild the list of letters to A, B, C, D, it has those 4 letters in it. The len function works on a list. Lists can be on any data type you want, or they can actually be hybrid on a variety of data types. So I can have the list x equals, or z equals 1, 2, banana. It does not matter. 1, 2, banana, that's fine. So there's nothing about lists having to be homogeneous in Python. So here we can actually construct a nested list of lists. So we construct the list A with A, B, C, and the list N with 1, 2, 3, and we can construct the list X, which contains both of those smaller lists inside of it. So here we've got nested lists, just like you'd see in Lisp, only square brackets and commas. If I try to access X0, I get the list A, B, C. And if I try to access X1, I get the first item of X0. Item 1 of X0, which is the second item, I get the B. Some important things to remember. A is ABC, and X0, X0 is also ABC. If I were to set if I were to set A1 to 1 equal to the empty list, that works. And then if I print A, A1 to 2 equal to the empty list, and then I print A, then I will have removed item 1 from the list. I could also have said A colon, I can replace it all equals A, B, C again. There we're good. And I can actually say del A1. So that'll remove the middle item from the list. And now if I print A, it's been removed. So you can, of course, assign a slice to the empty list, but sometimes it's easier just to say del and to give the item that you want to remove from the list, like this. Unfortunately, because I removed it from the list A, when I print X, it's also removed from the first list of X. Remember that first list of X is a reference to A. When I modify A, it affects X. So we have aliasing here. So again, if I were to remove that first item of A1 and then print X again, so changing A changes X. I think I might have deleted a cell. Interesting. So some things to notice. So multiple assignments. Okay, so here's a chunk of Python code and some things to notice about it. The first is multiple assignments. In this line here, we're setting the variable A to 0, and we're setting the variable B to 1, all in one line of code. So what's happening here is, we'll explain it later, it's sort of tuple unpacking and packing. But the idea here is you can assign multiple values to multiple objects in what I think is a pretty understandable syntax, right? Another thing is that any type, even if it's not Boolean, it can evaluate as true. Here we have a loop, and what's important to notice is that you have a header that ends in a semicolon and then an indented block of code. The block of code that executes is not delimited by a begin and an end. It's all indented the same amount. And so indentation matters a lot in Python. And when you want to display output, you use the print function. So here we have a little while loop. You can try to figure out what it does if you want to. It's the Fibonacci series. The first two values are set to 0 and 1. You're going to keep going until you have a number that is bigger than 10. You're going to print that number, and then your new A becomes your old B, and your new B becomes A plus B. So it's kind of convenient to be able to do multiple simultaneous assignments like this. For instance, if you wanted to swap two values, you can say x equals, let's say x equals 1 and y equals 2. Or we could do it like this, x, y equals 1, 2. And then we could print x, and we could print y. I'm hitting escape and A to add new cells. Now if I want to swipe them, I can just say x, y equals y, x, and they've been swapped, right? So if I can say x, now it's a 2, and if I say y, now it is a 1, right? So this multiple assignment can be convenient. So there's no swap function that you need. You just swap them like that. The print function in Python, it'll display whatever data type you want. It'll convert it to a string and display it. You can provide an end character. So if you don't want the string to end, the string to end in a new line when you print it, you pass the optional argument end, and I can set the end to be the empty string. So in this case, it prints 1, 2, 3. It does not go to the next line. It prints 4, 5, 6. If I wanted it to end with something else, I could have done an asterisk there, and it would have done 1, 2, 3, asterisk 4, 5, 6. Here's the example. It's the same code as before. for printing the Fibonacci series, only I'm setting the end character to be a comma, and I'm going up until the last number exceeds 1,000. So, and we get all on the same line with the commas in between. All right. So there are some gotchas. So one of those is this. I am going to pause the video for a second. Probably, well, I can't pause the video, but make a mental note. I don't like having the output in some of these cells. So I am going to go up to the kernel, and I'm going to hit restart the kernel and clear all outputs. I don't know why all of the outputs were in there. I must have been using this beforehand. So when I say restart the kernel, what it's going to do is it's going to wipe out the entire state of the Python interpreter. All of the variables, everything's gone. And this is like as if I never executed any cells. And now, I'm going to go to run, and then I'm going to run all the things above the selected cell. Now, actually, this is not going to work in this notebook because I have some cells which produce an error. So it'll actually keep trying to execute the whole notebook from top to bottom, but it stops when it finds a cell that has an error. So I'm going to catch up to where I was real quickly. I'm hitting Shift and Enter to move down the notebook. I may leave this in. I may go back and delete it from the sequence. So we did the Fibonacci sequence, and now I want to talk about a gotcha. So this is nice because we don't see the output before I execute the cell. So the first gotcha is, what do you think -3 squared should be? And the answer should be a 9. But remember that the order of operations is very high for that exponents. So it's -3 squared, right? So this is the same as -3 squared because the precedence is so high for the exponent, right? So if I actually want to get -3 quantity squared, I need to use parentheses, and then I'd get a 9. Okay. A little bit more on flow control. So we've seen a while loop. There are also if statements and for loops as well. Okay. So if you're going to understand one type of loop in general, it's best to understand how a while loop operates. But now let's look at some other things. First of all, in order to receive input from the user, Python has a function surprisingly called input. You provide a prompt, which is displayed on a line. It could be the empty string. And then the user types something, and the result of this expression will be a string of what the user typed. And then you can use the int constructor to convert that string to an integer and store it in the variable x. Right? Let's do that. So if I split the cell, then I can hit Shift Enter and execute that by itself. It says please enter an integer, and I'll do what is the checking? I'll do 3. And if I hit Escape B to create a new cell and I print X and Shift Enter, it's a 3. Right? So the result of input was a string and it got converted to an integer here. Let me just demonstrate that a little bit. Input, enter, anything. I do blah. It's a string. It's not smart enough that if I were to enter 3, that it would convert it to a string. So it gives me the string 3, not the integer 3. Older versions of Python would have tried to convert it to an integer, but they kept messing it up to the point where it was more confusing than just always returning a string. By messing things up, it would actually execute code that people typed, and it caused security problems. So, so this gives me an integer that is the result of what the user typed, And now we've got an if statement. So if that integer is less than 0, then it's going to set it equal to 0 and then print negative change to 0. If that integer is equal to 0, using the double equal sign, it's going to print 0. And if that integer is equal to 1, it's going to print single. And finally, if none of the other things are true, it's going to print more. So we expect it to print more. Okay. If I were to change it up here, I were to input a 0. Oops, 0. Notice how it stayed on that same cell. That's interesting. Now x is 0, and it prints 0. That's this one. And if I were to try negative 4, then it goes x is negative 4. It'll say negative change to 0. And if I type in x, I can see that it was indeed changed to 0. So it's sort of like coins going down a coin slot. It keeps trying each one of these LF branches until it finds one that hits. It executes that one and jumps out. Python does not have a switch or a case statement like languages like C, C++, Java, and C# do. If you want to do multi-way branching, you have to use if and elif, or invent some mechanism to do it yourself. There is no switch. The input displays the prompt and returns a string, as I said. So another thing that you can do in Python is a for statement. It's a for loop. The syntax is like this. You have the word for, a variable, and the word in, and a sequence, right? So there's a variety of different types of sequences that you can use in Python. Every list, for example, would be a sequence. In this case, W will take on the values cat, window, and defenestrate. I think that's from a Python skit, a Monty Python skit. And we'll print each word followed by the length of the word here. So that is a for loop. It went through each one of these things in sequence. Every loop in Python is a for each loop. It's not like Java, not like C#. There's just a for each loop. Those languages do have for each loops, but in Python they're all for each loops. So some advice about using these for loops. So one of the things that's worth mentioning is you should not modify any sequence when you're iterating over it, because that can cause weird race condition types of things. So just as a general rule, do not modify a sequence while you're iterating over it. Instead, you have to rely on some other strategies. Here we have a dictionary of users. We haven't talked about a dictionary, but hopefully it'll make a little bit of sense to you. At this point in time, if I were to type in users, this means that Sheldon is associated with the value active, Verdi is associated with inactive, Amal is active, Xavier is inactive, and Dennis is active, right? And if I were to say users and type in, for instance, Sheldon, it returns to me the value associated with Sheldon, which is active. So that's a dictionary. So if I wanted to iterate over each one of the key value pairs, then I would do it like, I've got a couple of ways that I can do it. So suppose you want to go back and filter out everybody who's active. One solution is to create a new dictionary and then to iterate over every key value pair in the original one. This gives you the key, this gives you the value. Then I can check if the status is active, then I add it to my new dictionary. So by assigning to a given element, that puts it in the dictionary. So the result of this loop will be a new dictionary called active users that only contains Sheldon, Amal, and Dennis. And so instead of modifying users by removing the inactive ones, I'm making a copy of the dictionary. And that's generally what you have to do to avoid modifying while you iterate. Another thing that you can do is much more concisely, many of the data types in Python will have a copy method. So instead of iterating over the original things, you can temporarily create a copy and iterate over its items. And that way modifying users doesn't cause a problem. And just like I did with a list before, if I want to remove from the dictionary, I can type in del and then enter the item I want to delete. So this will delete any user who is tagged as inactive from that dictionary. Right? So they both work, but the trick is, if I were to do users.items, I'd have a problem. So if I did this, now here's the trick: I may or I may not have a problem. The issue is, on some systems, in some situations, I might have a problem. So, well, actually, fortunately, I will always have a problem because Python has inserted the code to check it itself. So I'm going to modify this notebook before I put it up so that I show you what can go wrong. Before I show you what can go right. So trying to do this works. There we go. Boom. Boom. Trying to do that fails. Trying to do this works. Trying to do this works, but now the list has been modified. Okay, so that's just something to bear in mind. You can't modify a collection as you're iterating over it. Another thing is, I said that every loop in Python is a for each loop. If you want to iterate over a range of numbers, then you can create a range object. A range object acts like it's a list of numbers, but in fact, no list of numbers is ever stored. It just generates the next number you need on demand. It doesn't ever store it, right? So instead of using a list, you would use a range object. The way that range works, the operands work almost just like a slice would. You have a start, an end, and then a step. So basically the syntax for range is you have, if you look over here, range, you can have a start index, a stop index, and then optionally a step index. So if I wanted to go from 1 to 100 in steps of 2, then it would give me 1, 3, 5, 7, all the way up to 99, right? So that would be how you use the range. If you only pass in one value, then that value is interpreted as the end value, and it'll go from 0 up to stop -1. If I pass in 2 values without a step, then step will be set to 1. All right, so you can use these ranges to iterate over a range of integers, right? If I were just to type in range 510, it doesn't give me a list of numbers, it just gives me a range object. If I convert it into a tuple, which is an immutable list, then it'll generate that sequence and store them in the tuple. Here I can go from 0 to 10 by steps of 3, and you can see that it starts at 0 and it goes up in groups of 3 until it passes 10, and then it doesn't add that one, right? Here I've got the range from -10 to -100 in steps of -30, and so it'll go -10, -40, -70. All right, notice that in this case the start index is greater than the end index because I'm counting backwards. Right? You can use this as you would a normal for loop in other languages. Here we have the string Mary had a little lamb, 5 strings, and then you could say for I in range the length of A, and it'll generate the indices 0, 1, 2, 3, and 4, and you can print the corresponding value from that list. However, this is a non-Pythonic way to do it. Instead, in Python, if you want to get the index of each item and its value, you use the enumerate function. So the enumerate function takes any sequence type, anything that's iterable, and it'll go through each item, and it'll not only produce the item itself, but it'll produce the index of the item. So it generates the index and then the item itself. Over here is the documentation for iterable. Notice that it has a parameter called start. If I run this, anything I want it to, 10, 11, 12, right? So it counts up from start. So you can also name that parameter, which is more readable. I think it's easier to read when you actually name the parameter as start equals 1. Okay. So that's the enumerate function there. That's the better way to do this. If you just pass in one value, it starts at 0. The important thing to notice is that Range is a type of object that you see in many languages, including Java and C++. This is the way their for each loops works. There's the concept of something which is iterable, and the contract that it needs to provide is that it needs a function that gets an iterator. So in this case, in Python, the function iter gets you an iterator for an object if that object is iterable. So that includes lists, tuples, dictionaries, range objects, and some other things we'll see later. And then you can call the next function to retrieve the next object from that iterator. And each time you call next, you get a different object in the sequence. In Python, you tell when you hit the end of a sequence when a special exception is raised called stop iteration. So you keep getting the next thing until you hit the end of it. The way that you know you hit the end is that when you call next, it raises an exception. A lot of the Python functions, which are designed to be generic, will operate on any iterable. So you can take the sum of a range, so that's 0 plus 1 plus 2 plus 3. The constructor for a list takes anything that's iterable. The constructor of a tuple takes anything which is iterable. So you can convert from that type to any of those. So we've seen while loops and we've seen for loops. A little bit more about some stuff that you'll occasionally see in these loops. One of them is the word break. So here we have a nested loop. So for n going from 2 to 10, so 2, 3, 4, 5, 6, 7, 8, 9, and x goes from 2 to n, we're going to check. And if we ever find a case where n mod x is 0, then we're going to print n equals x times and then n /x. So when you add multiple arguments to print without a name, it's going to print them all separated by a single space. And if we ever print n equals something, then we exit out of that inner loop. Okay, so basically, if we can find a number that's less than n, so if n is if n has a factor, right? If n has any factor, we're going to print n equals that factor times something. If we go all the way through this, if we ever hit break, we're done. We're out of this loop and we go back up to the top. Now, if we get all the way through here without calling break, only if we don't call break, then we'll hit the else part. Okay, so that can actually, that's a surprisingly useful pattern, I think, right? So if you get all the way through this loop without something going wrong, only then does it execute this part, which means n is a prime number, right? So here we go. 2 is a prime, 3 is a prime, 4 is 2 times 2. So for each time it finds a factor, it prints what those factors are. And if it gets all the way through the list without something going wrong, that's the only time that the else executes, right? And if I were to put something just outside the loop, I always execute. Let me give it a little bit of prefix, right? You know, that'll always happen. But the beauty is this thing about 7 is a prime number. That only happens when you break out of the loop early. Okay. So for the other thing that you can do is continue. All right. So what continue does is it skips over the rest of the loop. So in this case, if it finds a number that's even, it will not process the rest of the loop. So this is called the Guardian pattern. It is actually a good way to program to put a bunch of continue statements up at the top of a loop, right? So you check a condition and continue, you check a condition and continue. The Guardian pattern is also used in functions, for instance. So before executing the body of a function, you'll check a bunch of preconditions and bail out of the function using an early return. Some people don't like early returns, multiple returns, but in the case of the Guardian pattern, they're very clear. It's a well-established and understood pattern for writing things. You'll often see that with continue. So you're trying to go through a loop, but you've got some complicated conditions for which you should only execute the loop. So you just bail out. The alternative would be to have the print indented as part of an if. And the problem is if you have multiple conditions, you end up having to indent once, twice, 3 times, 4 times, and before long, you're out of horizontal screen real estate, which is why you have these early bailouts, right? So what this will do is, if you execute that, it'll, if it finds an even number, it'll print that, and then it will skip over the rest of the loop. And if it doesn't find an even number here, it'll just print found the number 3. There's no else. Notice that there is no else. So continue is there in Java. We should be pretty familiar to it. Another thing that exists is a pass statement. Pass is just a no-op. You use that basically often as a placeholder. I plan to put something in the true condition, but I haven't gotten to it yet. I wrote this function, so I just haven't gotten to handling the true case yet, and so I do a pass. It's a no-op. Or I wrote this function, and every function needs a body in Python, but I haven't gotten around to giving it a body, so I'll just write pass. Same thing for a class. I want to write a class. Every class needs a body. I haven't gotten around to making it, so I'll just write pass. It's just a no-op. So we've seen some examples of this just above, but in Python, you group things into functions. And so the big things are the body of a function is indented, just like with a loop. Just like with the loop, the function declaration has a header that ends in a colon. You use def to define it, and the parameters are passed by what you would call object reference. So the parameters are passed by value, but all of the parameters are always references to objects. And so if those objects themselves are mutable, then you can change them. If those objects are not mutable, then you can't. So integers, for instance, are not mutable. Strings are not mutable. A lot of the things that you floats are not mutable. So a lot of the things that you think of as being primitives are in Python immutable, unchangeable objects. Right? So here's an example of defining the Fibonacci function as a function this time. We've seen this loop before. Now we're putting it inside a function called fib. So it does the Fibonacci series up to n. Some things to notice. You use def, the name of the function, open parenthesis, and the argument list, close parenthesis, and a colon. The body of the function is indented. The first line of the function is a string. This is a comment. This is a string. They are different things. This is a doc string. It is not ignored by Python. It means something special. If I put my cursor on, if I execute this cell, and then if I put my cursor over fib, that is the documentation that's printed in the help window, printing the Fibonacci series up to n. It means something. So these doc strings are actually the way that you document your code in Python. Everything else I think we've seen before. This is actually printing inside the function. So we printed this output down here when we called it. So this is the function call. Right? If we type in fib by itself, it is a function object. It's in the main module. It's main.fib then. Functions are first class objects. They are objects just like any other objects. You can assign a variable to a function, and then you can call that function that was in the variable using parentheses. If I call fib of 0, it returns nothing. It prints nothing. It returns nothing. You'll notice that there's a little blank there. If I were to come over here and if I were to type in the word none and hit shift enter, it does not display the result of that expression. If I were to type 0, it'll display the result of that expression. But none is Python for nothing, right? So when a function doesn't return anything, it is returning none. If I actually use the print function with that, you can see when I try to print it, using print, it prints the value none. The data type of that return value is of whatever type none is. It's of its own special type. Okay, so none is this special Python value like null in C++, although null is actually an integer 0. In Python, none is a special object of its own type that really represents nothing. Okay. Here we have a different version of the Fibonacci sequence, but instead of printing the results, it's building up a list of the results, and this becomes a little bit more useful. in general, if you write a function that's supposed to create a list of objects, you shouldn't be printing them. That would be a vast misinterpretation of what is being asked. Returning a list is much more reasonable because that becomes an actual object. You're actually returning the list of numbers versus displaying them to a user somewhere, which is, they're no longer usable at that point. So here we write the function. It begins with an empty list, and as it iterates through, instead of printing them, it's appending them to the end of that list. Then I can evaluate that for the value 100 and display the result, which should be a Python list. Right? So that's useful, right? We begin to see a little bit of using some of these list functions. Here is an even better way to do it, which is if you want to return a list, you yield each element one at a time using the special Python keyword yield. What yield does, if I hit Shift Enter, what yield does is it creates a special object called a generator. And a generator acts just like a range. It has not executed any of the code of that function beyond the first yield. So it got this far in the function and then stopped. If I want to evaluate the next value in that function, I can create an iter for f100. I can actually store it. if100 equals, right? And then if I type in next of that variable, it gives me the 0. And if I execute the cell again, I get a 1, 2, no, 1, 1, 2, 3, and then it should be a 5, and an 8. Right? So one by one, I'm kind of iterating over the different values of the Fibonacci sequence. But the beautiful thing about this is I didn't compute them all up front. So if I were to put a statement here that prints something each time, you'll see that it doesn't get executed. It doesn't get executed when I call the function, right? When I iterate the function to begin with, it still doesn't get executed. But each time I call next, it executes one line. It only executes the line once. Make sense? Now, if I want to get them all, then I can construct a list from it. It'll execute the line every single time I've already iterated through the first two. So once I iterate through them, I've consumed them. So this is the remaining items from that generator. So, I mean, if you want to write a function that's going to return a big list of objects and you never want to build the list if you don't have to, you use yield to return the next item one at a time. So that's it. Python has the yield function as well. A little bit more on defining functions. Functions have arguments that have default values, and then you don't have to pass them. So for instance, we can have a function here which keeps asking you if you want to continue until you give it a valid answer, yes or no. If you give it an answer other than yes or no, it'll ask you again. It'll retry it, retries number of times, and each time you fail, it'll display that reminder message. So you always have to pass in a value for the variable prompt, but by default, retries will be equal to 4, and reminder will be equal to please try again. So if we look at what happens, yes or no, does your mother know you're ugly? That's not nice. I can't say yes or no because I was so clever. If I give it an invalid value, it just keeps asking again. I'm not going to say yes or no. Oh, I did say no. Dang it. So it stopped as soon as I gave it a valid answer, right? But if I refuse to answer 4 times in a... What have I just done? I fat-fingered that. So in a Jupyter notebook, or anything like that, sometimes you can lose the display of a thing. You hit stop, the stop button up here, and it should terminate the thing that's executing in the background. unless it doesn't. So this can be, so when you're working off of a Jupyter notebook, it's actually a very convenient way to kind of prototype ideas, and it's sort of like a self-documenting paper that you can write. It's a little bit of executable code. And these are very popular for people in the sciences because you're capturing your methodology. It's like a workbook. It's a great way to iterate, prototype, and explore. And it has a lot of benefits. And here is a con, which is I've just put it into a broken state. The only thing I can do is restart the kernel. And I can execute everything above here except for, in this particular example, I've introduced some things that have errors. I'm not going to go back and execute them because I don't have to, right? But just so you know, what I just did is I restarted the kernel, which means this variable is gone, this variable is gone, they're all gone, okay? So here we're defining a function called askOK. Oh, I know what I did. I deleted the cell. I deleted the cell. Ha, that's why it went away. I deleted the cell that was producing the output. Yes or no, does your mother know you're ugly? X, 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 X. So what does it do? If the number of retries, if I run out of retries, it raises a value error, and that's what I got, invalid user response. Okay, so that can be kind of a useful function to have. Default values, we'll get into those a little bit deeper. So here we have a situation where we have defined the function f, and we set the default value of an argument to the variable I. What is actually happening is the variable's getting evaluated right here, and arg is getting set to 5, right? So if I set I equal to 6 and call f, it doesn't use the current value of I, it uses the value that it had at the moment the default argument was computed. Okay, since setting I equals to 6 didn't change the integer 5 into the integer 6, it changed the variable I to refer to a different integer. Right? So this is still referring to that same 5 object. Over here, it's a little bit different. Here we constructed a new list. It just created a new global variable, which is that list. It doesn't have a name yet until I give it the default argument name of L. And here I modify that global variable, that one global variable list. It's the same list every time I call the function. Unfortunately, it is the same list, but the list itself is changing. So if I call the function every time I call the function, that one list right here is getting modified. And so it's having a side effect of calling the function, which is usually undesirable. And if you do this in like PyCharm, you'll get a warning. Linters will often, static analysis tools will give you usually a warning when you do something like this, right? If you don't understand what's going on here, maybe ask in Piazza or something. But the idea here is whenever I just type a list, it creates a new global variable for that list temporarily. And it's that one variable. Here, there's one object for 5, but you can't ever change 5, right? Here, there's one object for a list, but lists can change. So that means that I can have side effects by calling that function. The pattern that you use to get around that is you don't set the default values to be anything that is changeable, mutable. So in this case, if you want it to be an empty list every time, you actually initialize it to none, and then inside of your function, you check if it's none, and in that case, you assign it to a new empty list. And so for each function call, this will generate a new and distinct empty list rather than reusing that same list every time. And now we don't have side effects. So this will be the pattern. When you have default values, you'll often, when you want to have an optional argument, instead of giving it a default value that is a mutable type, you'll give it a default value of none and then construct a new instance of the mutable type inside the function. Right. So the functions that you write can have regular arguments like voltage, but they can also have the arguments that have default values. And these are called keyword arguments because in order to pass the argument, you can pass in a keyword, a key, state, corresponding to a value like a stiff, right? And this is a reference to the Monty Python parrot sketch, which you should all Google if you haven't seen it yet. You'll notice that they have used a special word type because the syntax checker renders it in a different color. While it is a special word in Python, it has not been reserved, so it's okay to reuse it here for the name of an argument, right? So this has 3 keyword arguments and 1 regular argument. When I invoke this function in a variety of different ways out here, we'll see the different strings it produces. This is my comment about type being shadowing a reserved word. It would have been better if they had given it a name that did not clash with the reserved word. In Python, the convention to avoid a name clash is to use a trailing underscore, or you can just give it a name that's more specific to the context, like parrot type. If I spelled parrot correctly. Notice that action has the default value of boom, and voltage has the default value of no, voltage has the value I passed in, which is 1,000, and this parrot type has the default value of Norwegian blue. When I'm passing that argument, you can always pass arguments, whether they're positioned or not, you can always pass them with a name. And I think that very often passing it with the name can be produce more readable code. So often I will pass in the named parameter if I want it to be clear to the reader what that value is, so they don't have to go and look up the documentation. In addition, for the keyword, the other arguments, the other default arguments, you can pass them by name, and that allows you to pass arguments out of order. So I'm passing voltage, and I'm passing a value for action, but I'm not passing a value for state, which comes in between. So if I want to skip and pass them out of order, then I can just name each one of them. So I can do voltage and then action, or I can do action and then voltage. It doesn't matter because I'm using keyword arguments. Again, you can always pass them all positional, in which case the first one declared is the first one used, and then the second one declared. So this would be the voltage, this would be the state, and this would be the type, right? Yeah, you can mix them together. So you can have one positional and another keyword. That's fine as well. What you can't do is you can't leave out a positional argument. If it doesn't have a default value, it has to be passed. And then the other thing that you can't do is you can't position a positional argument after a keyword argument. So all of the keyword arguments have to come after the positional arguments. In addition, you can't pass 2 different values for the same argument. So either voltage is 110 or 220, it can't be both. Okay. And finally, if you try to pass a keyword argument that is not declared to be one of the arguments the function takes, then that will also be an error. So here's a link to the parrot sketch if you guys want to watch it. This is another example of one of those errors. You can't pass the same argument in twice. All right, so there is another thing that you can do with Python functions, which is you can create a variadic function. And a variadic function is a function that takes a variable number of arguments. In Python, if you want to take a variable number of positional arguments, then you can write an asterisk followed by the name of a list. And what will happen is when I call this function down here, each positional argument will, so kind will be stored in kind, but these next 2 positional arguments will get packed into a list here, right? So that works for your positional arguments. Your keyword arguments will get packed into this keywords dictionary so that I can look them up by name, right? So you use a single asterisk, and then you have your positional argument list, and then you have a double asterisk, and you have your keyword argument dictionary. Inside the function, I can access kind, my first positional argument, just fine. But now arguments is a list. So I could go through each argument in the list using a for loop, and print them or do whatever I want to with those. I can go for each keyword argument that was passed and print it. So here we go. Do you have any Limburger? I'm sorry, we're all out of Limburger. It's very runny, sir. It's very, very, very runny, sir. That is doing this, and then it's printing these two positional arguments, which were passed in because of this star arguments thing. And then I wrote this code that goes through and it passes all the keyword arguments as well. Michael Palin, John Cleese, and Cheese Shop Sketch. Okay. The order of the keywords depends on the order in which they're provided. That's true for both the dictionary, so Michael Palin was first, and then John Cleese, and then Cheese Shop Sketch, right? It's not in alphabetical order. Notice that C would come before S, okay? If I were to change the order, I change the order that they're presented in. So client change there. All right, some new things were added in Python 3.8, which was actually released this semester. I'm recording this video. Those things are separators, which mean they restrict the way that a person can use your function. So when you declare your function in the argument list, if you use a slash, then users are not able to pass the items on the left of the slash cannot be passed as keyword arguments, right? So if you want to present them being passed as keyword, you put a slash, right? If you want to put a star, then that means the items to the right of that star can only be passed as keyword arguments. So in between is the way that it normally works in Python. They can either be positional or keyword. But these restrict the way that other people can call your functions, and it allows you to write the main thing is to restrict the way that people use your functions, and it gives you the flexibility to change your API. For instance, if you don't know what the argument should be named yet, you can not let people use the keywords, and that way they aren't using a name that you're likely to change. Similarly, if you're not sure which order the operations should be in, you can let them use only keywords, in which case, again, the users are not locked down to a particular order. So, are you going to need to use that? I don't know. This is a normal argument. You can pass it by position or keyword. Now you can pass it by position, but if you try to pass it by keyword because it's on the left of a slash, you'll get an error. This is a function because it begins with an asterisk, comma. Then arg must be passed by keyword. If I try to do it by position, I get an error. But if I do it by not position, I'm fine. And then you can do it both. This is a problem because 3 needed to be passed by keyword. This is not a problem. And this is not a problem. But this will be a problem because the first one can't be passed by keyword, and it was. So this is a new feature mainly intended for people to develop an API. When you see it in your code, that's what it's going to mean. So arbitrary argument lists, so as I said, those are called variadic functions. Here you can see a function that it just concatenates all its arguments, right? So when I passed this list in, it arrived in here as a list, and then the list has a method called join, which, a string has a method called join, which will insert the string in between each of the strings in some list. Like, I could say star join A, B, C, and it puts a star in between each item in the list. So the argument to join has to be a list, right? And put the star in between each element of the list. Again, like I said, the argument has to be a list, and the items of the list have to be strings in order for that to work, right? So this will do it. Notice that there was no type checking. If somebody uses the wrong type, you'll get an exception. Since there's no compilation phase for this, it's a high-level language, it's scripted, that's all you can hope for. Yeah, you can change the sep here, earth.mars.venus. So they just wrote a concat function. So that can be useful if you want to write functions that are variadic, right? I'm calling the range function with two arguments, 3 and 6, and it's generating the range 3, 4, 5, 6. But sometimes, programmatically, you'll want to put your arguments in a data structure like a list, and then pass them to a function which does not take a list. So how can I convert a list into a series of positional arguments? And so the asterisk in the declaration of a function packs your arguments together. The asterisk, when you're calling the function, it'll unpack a list of arguments. So if I've already got the arguments in a list, if I write a star in front of its name, it's as if I'm calling the function range with the first argument being a 3 and the second argument being a 6. So it'll generate the same range, right? Similarly for the keyword arguments. So we've got this parrot function from before. If I know what I want some of these values to be, I can actually store them, or all of them, I can store them in a dictionary. And instead of passing all of the keyword arguments, I can just unpack the dictionary using 2 asterisks. How is this? I need to execute that cell. How is this useful? Well, it could be the case where you have, where you build up the argument list for a big function one piece at a time algorithmically. And so you just store the values of different arguments in a dictionary before you call the function at the end. This is used, for instance, when you're doing some geospatial processing. Okay. Okay, lambda expression. Okay, yes, we talked about lambda expressions before. Python also has a lambda expression feature. Here you use the keyword lambda, followed by the argument list, followed by a colon, no parentheses around the argument list. And then you write an expression which is evaluated by that lambda function. This constructs a new lambda expression, a new function object right there in the code, which can be returned by it. This thing which is temporarily created is called a closure. And the reason it's called a closure is because not only is this a temporary function, but this temporary function is referring to a variable n, which is not global. It's in a containing scope. So somehow I need to store and tack that external reference onto the function that gets returned. So it's not just a function, it's a function with its own data. So that's called a closure. So here if I call the make incrementer function, it returns this object f, and f itself is a function, right? Notice that the fact that it has access to the locals of make incrementer happens to be indicated here in its name. That's interesting. I can invoke that function with the argument 0, in which case I get 42 plus 0, because when I called up here, I passed in 42 as x. And if I pass in 1, I get the 43. So this function f, it not only is a function, it's got access to that data as well. It's keeping that data as part of it. So that's called a closure. Function chunked together with some data potentially. Here we're constructing a list of tuples. So again, a tuple is a list that you can't modify, and they're wrapped in parentheses. It's called pairs, and I can sort them. The sort method of a list takes an argument called key, and again, we'll talk about some of these things a little bit later, but it takes an argument which is the thing that you compare, right? So the key, the function key takes an element of the list, which in this case the element is the entire tuple, and it's supposed to return the thing that you use as the basis of your comparison. And in this case, I'll return the second item of the list, so the strings 1, 2, 3, and 4, right? So if I go to sort that list, it'll compare it in order by the strings. F comes before O, comes before T, and H comes before W. So the actual numeric quantities are out of order, but the strings are actually sorted in order because this lambda function is plucking out that of the field. And this is one way that you can use lambda functions, is you can write a routine, and part of the behavior of that routine, you're letting it be a parameter to the function itself. If we did not pass in the key function, then it would have sorted them in lexicographic order. By the way, sort will sort the list in place. So if we don't pass in that key function, it does what we expect, which is it appears to be sorting things by the first value of the tuple. In fact, if I were to append another tuple that begins with a 3 but then has an A, that will come before the version of 3. I don't know what I just did. Hold on. There we go. That'll come. Oh, I've executed this cell multiple times. Okay, so let's do this one. Pairs. Then I append the 3 and sort it. And now I look at pairs. So what happens is 3 with an A comes before 3 with a T. And that's because what it does is first it arranges them by the first item of the tuple, and then it goes on and arranges them by the second item of the tuple. Most collections in Python will sort themselves or compare themselves using a lexicographic order like that. So first you compare the item at index 1, and if index 1 is equal, then you compare the item at index 2, and so on, until one of them is either longer than the other, or until one of them is greater than the other. So documentation strings. This cell does not belong there. As I said, the documentation is these strings here. They are not comments. They are help strings. They get stored with that function object as dunder_doc. You can print that method, that thing, and also if I click on the function name here, my function, it's what shows up in the help window with most tools. Also in Python, if I write my function with a semicolon, I get that doc string. The intent here is to explain to people how to use your API. It's kind of ingrained into Python. Another thing about functions and data types and in general in Python, you will often hear people say that Python is a language which uses something called duck typing. Variables do not have types in and of themselves. Instead, the type is really associated with the object referenced by the variable. So a name in Python, there's no contract that says it always has to refer to the same type of thing. It's perfectly okay if I say x equals 3 and then I print x, and then later I say x equals quote 3, and then I type in x, and x used to be an integer, but now x is a string. By the way, if I want to see the type of an object, I type x, all right? X equals 4, type x, all right? So it's okay for the data type referenced by a variable in Python to change. It is a dynamic language in that sense. However, when you have a completely dynamic language like this, it does pose certain robustness problems because you can't run static analysis tools over it to check whether you're using your types incorrectly. In order to remedy that, Python 3 introduces a syntax that lets you annotate your variable names. The language itself ignores these, mostly. However, they are preserved as a type of metadata for your program, which can be used either by static analysis tools or by your own library to do different things. So here I'm declaring a parameter ham, and then I say colon str. So it's adding metadata to that, which says I expect it to be a string. Python, again, it doesn't restrict it. I can assign anything I want to it, but it expects it to be a string. So if I were to type in before the return statement somewhere, ham dot, it should know that what I'm looking at is a string if it can parse that annotation, right? I'm not quite sure that this particular IDE is smart enough for that, right? And then again, so this would be the way that you add type annotation to parameters and also variables. So in here I could say x colon int equals 0, right? And I've added this type annotation that I expect this to be an integer. Again, I can also document what I expect the return type to be using an arrow. So indeed, Python is a completely dynamic language, but if you ask for it to do type analysis, you can get it to do it. You just need to actually annotate things with the types. It's often a good idea to do that. You'll find that I think I will tend to type annotate because it helps me get the documentation in my editor to be better. So as you can see, those annotations are available in the function as a dictionary. So it knows that ham is supposed to be of type string, eggs is supposed to be of type string, and the return is supposed to be of type string. Yeah. Okay, so that's going to wrap up our discussion of functions. There are some things that we didn't get to. I didn't get to talk about things like decorators, and I don't think we talked about local functions, but let me just show you that right here. So escape M, local functions. So I can write a function called add3. You know what? Let me do this. So this wasn't here in the list, but I want to put it in here. So there is a technique in dynamic programming called memoization. And so suppose I wanted to write a function called fib. And the idea is that fib generates the nth Fibonacci number. So I could say k, right? And the way that it's going to work would be really simple. If k equals 0 or k is equal to 1, then I'm going to return a 1. Else, I'm going to return a fib of k minus 1 plus fib of k. Yeah, k equals 0 or k equals 1. And that's your naive definition of the Fibonacci sequence. You don't often see people do that because in order to generate the first 8 Fibonacci numbers, in order to generate the 8th Fibonacci number, I have to generate all of the Fibonacci's up to 8, and that can be quite slow. So you can see it taking quite some time to compute. and it actually ended up with a recursion error. Did I mess it up? Let me try doing a smaller one, fib 5. Oh, okay. K equals 0 or K equals 1. There you go. Ah! Wait a minute, this is stupid. That's infinite recursion. So it's got to be k minus 2 times fib of k minus 1. Okay. So fib 5 should generate the 5th Fibonacci number, which is 8. If I say fib 10, it should generate the 10th Fibonacci number. I don't know what it, okay, it's 89. And if I say fib 30, it should generate the 30th Fibonacci number. Well, they get big quite quickly. Let me say fib 50. Now I'm waiting for a while. I mean, this is really slow. And if you studied this when you took your algorithms class, you know that the running time of the Fibonacci sequence recursive method like this, it's going to be an exponential time algorithm. It's going to actually take 1.6 raised to the 50th power time to run. So it's order 1.6 to the nth. So it's an exponential time algorithm. It's really slow. As you can see, it's still computing the 50th Fibonacci number. So this is a highly inefficient thing. As you saw, it worked okay for small values, but I just interrupted it. But there's a value at which it just becomes completely unmanageable. So there is a technique that we learn about in our algorithms class called memoization. And in Python, there's something that you can use called a decorator. So I'm going to create a decorator called memoization. And the idea is that I take as a parameter a function f, right? And what I do is I'm going to return a new memoized f function, which takes as input an argument. Let's just say I take an argument list, right? Any set of arguments, right? And then it takes a memo, and the memo is going to be a dictionary, but here we go. It's going to be dictionary, but dictionaries are mutable, so I set the default value to be a none. So now what happens here is this is an outer function, and this is an inner function that has access back to f. So I can actually just create one function inside of another like that. And the idea here is I'm going to say if memo is none, then memo there we go. I got to indent it a multiple of 4 spaces. If memo is none, then I'm going to set memo equal to a new dictionary. And to create a new dictionary, I can write dict by itself like that, which creates a new dictionary, or I can do 2 curly braces like this. So if you remember in memoization, what I'm going to do is I'm just going to store the arguments if they've been passed in already, right? So I'm actually not going to handle keyword arguments for this one, although it might be possible to do it. So if memo is none, memo is the empty list. Okay. So else, no else. I'm going to say if args in memo. So if the arguments are already in the dictionary, so in is the operator which checks to see if the arguments are in the dictionary, then I'm going to return memo of args. I'm going to return the result that's associated with the args. Otherwise, since it's memoized, I'm going to set I'm going to make this even easier. If the arguments are not in the memo, then I'm going to store in that memo. Not in is an operator of Python, which it looks like two words, but it's one operator. If arg's not in memo, it checks to see whether a key is not in the dictionary. Then I'm going to set memo args equal to my original function. Well, I'm going to call myself recursively. I'm going to call f. All right, so that's it. I only evaluate f if it's not in the memo, and then I'll just return memo args. There we go. So, and then I'm going to return memoized f. So, what does this do? This creates a local function, which before you invoke this original function, it first checks to see whether it's in a memo, right? So this function would be called memof. For instance, over here, if I were to call, if I were to set fib equal to memo of fib, and then if I were to say fib of 50, I think it was before, if I've done it correctly, this should actually finish quite quickly. No, it won't finish quite quickly because I need to pass the memo. Nope, I can't do that. Okay. I probably need to delete this piece of code. I got completely sidetracked. So I'm going to delete this. No discussion of local function in the video. I need to go back and delete that from the video. Okay. While it's good to know, I don't have a good example handy to demonstrate it, and I'm a little bit too tired to come up with that one correctly right now. But it's really neat. So you can do something in Python where you could have a function that automatically generates a memoized version of another function. So go back and edit that out. Data structures. So now we're going to go into some of the built-in data types of Python. To begin with, we're going to look at a little bit more on lists. So here we have a list of fruits. One of them is that list has a function called list.count. List.count tells you how many occurrences of a value there are in the list. So in this case, there are 2 instances of the word apple, 0 of the word tangerine, and 2 instances of the word banana. That can be useful. That's used in bag data types, anything that can have duplicates. List.index will give you the index of the next occurrence of an element. You can pass a start index, so it'll find the next occurrence after start. You can also pass in a stop index, and by default, stop is set to the maximum allowed possible size. Here we can find the index of the first occurrence of banana, and then we can find the index of the first occurrence of banana that begins after that one. So you can use that to one by one step through occurrences of objects in a list using that start parameter. If you want to reverse a list, there is a list.reverse method. It will actually reverse the list in place, right? So it doesn't return a value, it returns none. So here you've got a list of fruits. If I invoke the reverse function and then I look at the list of fruits, I'll notice that they are in reverse order. If I wanted a copy that was in reversed order, I would type in fruits, colon, and I would use slicing. I could go from 0 to the length of fruits, by 1, but if I want to go in reverse order, then I would stop at the end, which is length of fruits minus 1, and go down to 0 by steps of 1. So here I can use slicing. Start from the last element, go all the way past the beginning element, and do it in steps of 1. Now, this is kind of clumsy looking, but remember, if you leave a parameter off, they usually have good defaults. So this means go through every element of the list in steps of 1, and if I want to go in reverse, go through every element of the list in steps of -1. So this is reverse shallow copy. Okay, so that gives you a reverse shallow copy. You might find this sort of syntax useful. Remember, start wherever it's best to start in this case, which will be the end of the list, end wherever it's best to end, that's just before the beginning, and move in this direction of -1. Okay, so that's pretty useful. Here, let's take a peek. It should be back in the correct order again. So it went from orange to banana, then we reversed it, it's banana to orange. I made a copy, which is put back in its original position, but the actual list is left the same. So, of course, we've seen append. You can add to the list. I used a semicolon to put 2 statements on one line here. The sort function, we've seen it. It sorts things in ascending order. You can pass in a key function, and you can pass in reverse if you want to sort it in descending order. So here you can sort a list of fruits. It does a lexicographical sort, and I believe it's stable, if you know what that means. You can remove from the end of the list, so pop removes from the end. Again, you can reverse in place. So it doesn't actually change the list if you do that slicing. It's possible to, I don't know why this is here. It belonged where it was. Get rid of that. So you can use lists as stacks. So for instance, you can create a new list like that to push to the end. You just call list.append. So I added a 6, I added a 7, I popped a 7 off, I popped the 6 off, and I'm back to 3 again. So it's really efficient to use a list as a stack. However, if you want to use a queue, a list is not such a great choice. Here you've got the list Eric, John, and Michael, and to use it as a queue, you might keep trying to insert to the beginning. So you put Terry at the beginning and Graham before Terry. However, the problem is inserting to the beginning is not very efficient because you have to shift everything around. Here we see an example where we are trying to remove from the beginning of a list. So if you were trying to add to the end efficiently and then remove from the beginning, then you'd find that with the list data type, that is not such an efficient thing to do. This took us 11.6 milliseconds, plus or minus 131 microseconds. So it's not that efficient. Just so that you understand what's happened here, at the top of the loop, I used double percent time it, which is an IPython magic function. So it's not normal Python syntax. This is a special instruction that goes to IPython. And IPython has some special routines that let you save the contents of a cell as a file or profile, that is time the code inside of a cell, which is what I'm doing here. It's doing 3 repetitions or 3 runs because I did -R3. Okay, so this is not Python. This is an instruction to Jupyter, to IPython, but this is the code that generated 1,000 and then removed 1,000. Now, if you actually do want to use a queue that lets you add or remove from the other end, from the beginning, then you can use a double-ended queue. In a double-ended queue, you can efficiently add and remove from both ends. So here you construct a double-ended queue. I can add Terry to the end if I spelled Q right, and I can add Graham to the end, no problem, if I could spell Graham right. So I add a Carry and Graham, and then I queue. The queue, and now I can remove from the beginning Eric, I can remove from the beginning John. So the order in which you remove, so in this case you can just keep adding to the right end with append as normal as a queue, and it works like a queue because when you remove off of the other side from the left. Now with a double-ended queue, if I go through and I created a queue of 1,000 items and then I removed them all, instead of almost 13 milliseconds, I'm down to 1.38 milliseconds, so much faster. Okay, so if you want to use a queue, use a collections.dec. From collections, import double-ended queue. Another thing here, when we talked about scheme, we talked about higher order functions like map and filter. And in Python, you also have functions like map and filter. But you have an even better way to build lists. So here's your sort of naive default way to build a list. You create an empty list, you use a for loop, and for each item you'd like to be in the list, you put it there, right? So basically what we're doing is we're taking a list of 10 elements, and from that we're creating a new list of 10 elements where each one in the output list is the square of the one from the input, right? So here, in this range, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then here you have 0 squared, 1 squared, 2 squared, which will be 4, and so on. So this gives you all the squared numbers, 0, 1, 4, 9, up to 81, which is 9 squared, right? So this works just fine. But number one, it's inefficient. Number two, it's a long piece of code. It's a lot to read, it's a lot to type, and it's a lot of opportunities to make a mistake. And you're not telling the interpreter as much about your intents. So intent, or the reader as much about your intent. Here's a little bit more of a direct way to do it, which is to say we're trying to take this range and we're trying to map it to a new range using this function to do the mapping. The beauty is if you use the right function for map, you could use the built-in function map, but you can also import a function named map. You can override it with a function that you import from a library called multiprocessing or from a library called Dask. And if you do that, then map will it'll actually be running across multiple cores on your system. If you have 40 cores, if you use Dask, then it might even be using multiple nodes in a cluster, and you could be running across thousands of nodes in parallel. So Python actually does have the features to run these things asynchronously and distributed if you use map. So that's kind of nice. Yeah, you pass that function. And then, of course, the result of this operation of map is going to be a generator object. So the results will come back as soon as they're ready, and then you can read them off in order to build a list. Right? So in this case, you get the same result, but it's much more flexible. It's much more abstract. This one you could not easily parallelize because the code would have to analyze. Any attempt to parallelize this would involve analyzing your code. This one, any attempt to parallelize it, all it has to do is replace the map function. Here we see an even more direct way to say it, possibly not as easy to parallelize though. And this is called a list comprehension. And the idea is that you take this for loop and you flip it around. So much like the ternary operator flips things around, this one you put the body of the for loop just before the for loop itself. And the idea is that it's going to go through this range, and for every item x in the range, it's going to evaluate x squared. So you kind of can imagine that this should have been the body of that for loop. And this generates that list in place. And it is even more concise than this, although not as generic in a sense. Squares, right? It gets the same results, right? So really this is the for loop that builds a list. The Python interpreter knows what you're doing here. So there's some opportunities for the Python implementer to be efficient. And there are libraries which can actually take advantage of these as well. I use this all the time because it's much easier to think that way. It's much more concise. In general, though, you avoid writing. You always try to avoid the loop in Python. So this, I would argue, is the best. But this is easier. Okay. This one doesn't use a for loop. That makes it better, because that means you can distribute the work over multiple processors, multiple cores in the future if you want to. This one is the easiest to type, and that usually wins. So it can get more complicated. Here, again, you're going for x in 1, 2, 3, and then you go for y in 3, 1, 4, and then you can even tack a filter at the end if x is not equal to y, right? And so then inside that if statement, you'd say x, y. So basically, you have to read the list comprehension starting not at the first thing you see, because the first thing that you see is the body of the loop, right? Here, x gets created first. For each instantiation of x, you get a different instantiation of y, and then you filter, and then only after all of that has been read, then you come back here and you evaluate this expression, which returns the tuple x comma y, right? So when I do that, you get all the cases where x is not equal to y. You got 1, 2, 3, and 3, 1, 4, right? So you could check if that's the case. This down here is the same exact code. Notice that the expression that you're adding to the list is here in the body, but I don't have to call combs.append every time, and I don't have to initialize combs to an empty list, right? So essentially it's the same thing. You get the same exact result. Here it's packed into one line, and you could argue about the readability, but once you get used to it, this is very readable. It's XY. This is the same notation that your math textbook uses in order to define sets, right? So this is the same exact notation you'd see in a math notebook to define a text. It's the set x comma y for each x in this set and for each y in that set, subject to the constraint that x not equal y, right? So it works nicely. Here you can create a new list, which is the double of every item in the list vec. I don't know where the list vec was created. Let's make one. Why not? So that is x squared for each x in vec. This is, let's make vec have some negative numbers. There we go. That's x squared for each x in, no, it's x times 2. Yeah, that's x times 2 for each x in vec. I thought it was 2 asterisks, it's just 1. Here, we're just pulling out the positive ones. Here, we're getting the absolute value of each item in vec. So it's pretty useful. It's a really concise way to do it. you can ask yourself, is that more readable or is this more readable? Of course, this doesn't compute it right away, so I have to convert it to a list. It computes it on demand. So you can ask yourself which one is more readable. I think that this one is actually easier to read. Okay, so here, yeah, you're just going through each item and invoking a method on it. That's fine. It's stripping the white space. That's something you'll often want to do. Here you're creating tuples. The second item is the square of the first item right here. So those become very easy to write down in Python. So you're saving yourself 4 lines of code each time, and that adds up to very short and simple code. And semantically, it maps to the way that you would write it or read it in a textbook, and that's extremely valuable. Here you've got a problem because if the result is supposed to be a tuple, you need to put it in parentheses, right? So it needs to understand what's meant by the comma here. Once it sees an item and a comma, it thinks you're building a regular list, and you can't mix together listing the elements with using comprehension, right? So in order to fix this, you need to do what was written up here. Put it in parentheses. So here's an example of using a list comprehension to flatten a list. So here we know we've got a list of lists. So what do? We go for each item in vec, and then we go through each number in the sublist, and then we just return the num using the list comprehension. So it's easy. You just have a double for loop, and then you put the result there. So we flattened it all out. The math module includes a constant named pi, and here we're going to go through and round pi to a different number of digits, and we'll have 3.1, 3.14, each an increasing number of digits. It's fine. You can put whatever you want to in your expression here. Okay. So you can have a list comprehension of list comprehensions. So the example here is a matrix. So, it's a list of lists. It's supposed to be square. Again, Python, it has an array library that you can use, but sort of no built-in array type. So all of their lists are implicitly jagged. The way that you get around this is you use the NumPy library, which defines a good array type. The Python standard library also has an array type, not as good. Are not as broadly used, right? So here we are creating that 2D matrix. If I were to display it, that's what I get. I'm assuming each one of those is supposed to be a column, and then we can transpose the matrix, which means you exchange the rows and the columns. So here's a loop that would do that. You create a new list of lists to be the transposed matrix. You construct a new list to be the ith row for I equals 1 to 4. And then you go through each row of this matrix and you pluck out the ith element to add to the transpose row. So the first transpose row is going to have the 1, the 5, and the 9. The second one is going to have the 2, the 6, and the 10, and so forth. So this builds a row of the transpose, and then you just keep appending them back to the transposed matrix. So if we run that, we get this result. If you want to debug it, there's a couple ways you can do that. The easiest way is to use the Python breakpoint function and hit Shift-Enter. And now if I list the lines of code, we can see I'm right there. If I hit N, it takes me to the next line of code. Oh geez, of course it doesn't work when I go to demonstrate it. The other thing I can do is I can say, you know, it's possible to put breakpoints in Python code, but I think that the breakpoint can't actually be at the top level of a cell. So maybe I can put a breakpoint right here. And it's just one of those little glitches you got to deal with. So there's a breakpoint. If I hit L, it'll list the contents of the code. The arrow points towards the next thing it's supposed to display. If I type in a value like transposed, it'll display that matrix. Right now, I is equal to 0, and I can hit the N key. That takes me to the next line. If I hit the L key, it'll show me a few lines around where I am. So now I have a new variable called transposed row. And if you haven't used a debugger before, it's worth knowing how to use them, especially a command line debugger. If I hit the N key, it goes through that thing, and the next thing it's about to do is append row I. So what is row? 1, 2, 3, 4. So because we were iterating, if we look at everything, we're iterating for each row in the input matrix, right? So row I is 1, and I hit next, and now I'm going to go on to the next row in the matrix, and if I look at row 5, 6, 7, 8, that should be the second row of the matrix. It is, and if I look at transposed row, it currently, if I could spell right, this is why I need an autocomplete. It should currently have a 1 in it. Yeah, so if I hit the next key, it's going to append row 1. Now if I look at transposed row, it has both the 1 and the 5. And if I keep going with the C, it's going to work as expected. I'm going to quit the debugger with the Q and get rid of that breakpoint. So you can use that thing that I just did to debug code if you want to really know what's going on. However, if you do really want to debug the code, I would urge you to use a real IDE with a real debugger so you can step through the code like PyCharm. Here's the same exact stuff, only to build each one of these transposed rows, I'm using a list comprehension. So the selected text right there has been replaced by this list comprehension right here, right? So what is it doing? It's going for each row in the matrix. For each row in the matrix, it's computing row I. It's computing row I, and it's appending them all to a list. So it's building the list. Okay. So then it takes the transposed row that is built here, and it appends it to the transposed matrix. Right. So this line is building a transposed matrix. But now, when we look at it, we have a for loop, and we have an expression. So we can just write a double list comprehension. For I in range 4, we're going to do this generated list. So it's just a nested list comprehension. And so that quickly we can write the transposed matrix. However, there is a one-liner. So basically 159 is the first row, whereas 159 used to be the first column. 4812 is the last row, whereas 4812 used to be the last column. Using the Python functions list and zip and the argument unpacking trick, it is possible to write a better solution like this. However, I would not even use this. I would use the NumPy library. Because when you're dealing with matrices and so forth, it makes a lot more sense. So I would just say np dot transpose. Give it a second to catch up to me. So what the NumPy library has is it has an array data type, and it very efficiently operates on arrays. Plus, it gives you a whole bunch of function names that already do what you want to do. And this is the way that Python programmers work. You really don't reinvent the wheel. You use the huge amount of library codes that exist. And very often, you're mostly using the NumPy package. So there's a few more things I want to cover. The del statement. Again, if you have a list and you want to remove an item from it, you can use the del statement. So this began with a -1, and I deleted the item at index 0, and now it's gone. You can delete a slice. So from 0, 1, 2 would be 333. So it'll delete the two 333s, and they're both gone, right? So deleted those two. Here we can delete everything from the list. The list still exists, but we've removed all the items. And then here we can delete the list itself, in which case that name is no longer valid, right? So you've removed the variable. It's gone. You can't refer to it anymore. So that's the del keyword. That's pretty useful. Again, we've been using tuples, so we'll dwell a little bit on what a tuple is and what they look like. If you start listing values in Python separated by commas, it's going to create a thing called a tuple for that. In this case, t is set to a tuple, and I can use t0 to access the first item, t1 to access the second, and t2 to access the third in this case. So if I look at t by itself, it is the tuple 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, and hello. You'll often see this used when, for instance, if you want to return multiple values from a function, you'll just say return and then values separated by commas, which is it's just creating a tuple to return. You can nest tuples. So t is a tuple and u is a tuple whose first item is t and whose second item is all of this stuff. That's fine, right? It's a tuple of tuples, but tuples are immutable. So now that I've created this tuple, I can't change the item at position 0. So like strings are specifically of characters, but like a string, tuples can't be changed, right? However, even though the tuple can't be changed, the things inside the tuple might be mutable, right? So I can't change which list comes first, but maybe I could modify that list, right? So for instance, v0, 0 equals a. That was valid, right? Why was that valid? Because I didn't change the tuple. The first item of the tuple is still the same list. The second item of tuple is still the same list. What was changed was the contents of that list. Okay, so that's important to keep track of. So here's a note on some of the syntactical tricks about a tuple. If you want to create an empty tuple, let's do this. Yeah. Okay, whoops. I'm trying to split the cells. So if you want to create an empty tuple, you can just use a pair of parentheses like that and take a peek at what you get as a result. If you want to create a tuple with one element in it, you just put a comma at the end, right? So this creates the tuple singleton, right? Now, usually when you'll typeset it, you'll put a parenthesis around, you'll have a single item and a comma at the end, right? Now, if you didn't put the comma at the end, then it is not a tuple, right? So that's important. A tuple with a single element needs a trailing comma. The length of empty is 0. The length of singleton is 1. I can look at it with that trailing comma. The neat thing about a tuple is if you have 3 values in a tuple, you can unpack them into 3 variables like this, right? So here, if I look at x, y, and z, well, whoops, y and z, there we go. it removed, so the idea is as long as the items on the left-hand side of the equal sign are the same as the items on the right-hand side of the equal sign, you can unpack them. Now, you might recognize this from earlier in the video when I said you could do multiple assignments. Really, all multiple assignments is doing is you're putting a tuple on the right-hand side of the equal sign and you're unpacking it to a tuple on the left-hand side of the equal sign. So that's pretty syntactically useful. Moving forward, so you've got lists, we've got tuples. We also have sets in Python. A set in Python is going to be delimited by curly braces, and you're going to have the items inside of the set listed like that. The ordering, though, can tend to get ruined somewhat in a set. So we've got orange, banana, apple, and pear. So you notice that they're no longer in the same order that they were before, because in a set, order doesn't mean anything. In order to check whether one object is inside of a collection, you use the in keyword. So orange, the in operator, checks for containment in things. So is crabgrass in the set basket? That would be false. All right, so Python uses an in operator. It gets rendered syntactically because it means something. You can convert other sequences into sets. So if your values are in a list or a string, then you can construct a set from them. And when you build a set from them, all of the duplicates will be removed, but the order will be messed up, right? So here you can get just the unique letters that were in that string A because we converted A to the set, to a set. You can do the set differences. This means the same thing in math as A/B. You can do the union. Remember, there's a conceptual relationship between the union and or. So this gets any item which was in A or in B. And you can do the intersection with and. So this is any item which is in both A and in B, right? So there's really short notations to do these big operations on sets. And you can do the exclusive or operator. So this is in A or B, but not both, right? So you can also use a set comprehension. Here is, it just looks exactly like a list comprehension. You're building a set though, right? So this builds a set out of the elements X. Where those X elements come from, they're generated by this loop. It should be pretty straightforward. Here we've used the not in operator. Even though it's two words, it's one operator. It's just the complement of the in operator, right? So there we have D and R. Right? So dictionaries. A dictionary looks a lot like a set, only instead of just listing the keys, you do key and then a colon and then a value associated with the key. Oh, incidentally, you can also construct the set like this. All right, so you can build a set using the set constructor. You can build a dictionary using these curly braces or using the dict constructor, right? So here we're setting a dictionary of telephones. Jack is associated with 4098. Sape, I don't know, is associated with 4139. And afterwards you can, so we construct the telephone, and let's take a peek at it. So there's the telephone. We look at a peek at it. It's this dictionary. Jack is to 4098. Sape is to 4139. By assigning to an element in the dictionary, it automatically adds it. So this added Guido and associated the value 4127 with it. So anytime a key wasn't already in the dictionary, by trying to write to it, you automatically create it. Here you can look up a value and it gets the result associated with it. If you want to delete an item from the dictionary, you can use the del operation. And yeah, so we deleted SAPE, he's gone, and then added IRV, right? You can take a dictionary, and when you try to, so whenever you try to iterate over a dictionary, you only iterate over the keys, and it returns them in the same order that they were added to the dictionary. So the most recent thing added was IRV, so that is the last item in the dictionary, right? Guido was added after that, and Jack was added before Guido. So they're kind of listed in order of insertion for a dictionary. Converting it to a list did the same thing it does for anything that's iterable. It just made it a list of the values. But iterating over a dictionary only iterates over the keys. If you want them to be sorted, you can use the sorted function, which generates a copy of the list that has been sorted. It does not modify the original list itself. If you want to sort the list, you can use list.sort. So sort versus sorted. What's the difference between sort and sorted? Sorted returns a copy that's been sorted, and sort will actually sort a list in place and not return anything. The in operator works for lists just like it did for sets. However, it is less efficient on a list. It works for, we're not talking about lists right now. The sorted operator does not just work on a list. So tell is a dictionary. The sorted works on anything that is iterable, and it puts its result in a list, right? So it's the same as list tell dot sort followed by return. It's the same as saying x equals list tell dot sort. Right? So it kind of saves you some keystrokes using sorted. Here you can use the in operator to check whether the key is in the dictionary, right? And it is. Here you can use the not in operator to check to see whether it's not in the dictionary. Jack is in the dictionary, so this is false. You can construct the dictionary using the dict constructor, in which case you pass a list of key and value pairs, and it'll construct a dictionary from it. You can also use a dictionary comprehension, which is associating x with x squared, and it's doing that for x in 2, 4, and 6. So again, that's a dictionary comprehension. It should make sense. The only trick here is this is a key value pair. It's just the two values separated by a colon. And finally, you can pass keyword arguments as long as the keys are simple strings to the dictionary constructor. And what it'll do is it'll take all of the keyword arguments and it'll store them right in the dictionary. All right? So that's dictionary. That's pretty useful. Now, looping, if you're going to try to loop over things in for instance, a dictionary, there's a couple of options that you have. Remember, when you iterate over a dictionary, you're only iterating over the keys. If you want to iterate over both the keys and the values, you can iterate over, you use the items function, right? So this knights.items returns a sequence of tuples. And here we're unpacking those tuples into their key and value parts. And so we can print each key and valid. So Galahad, the pure, Robin, the brave, right? You can also, of course, just like, so this isn't to do with dictionaries, but here we're looking at a list. We already talked about the enumerate function, which is useful if you want to have the index in addition to the list items. That's a good, popular, correct way to do things. As I said, if you wanted to start at 1, you could pass in start equals 1, and then you get 1, 2, 3. I'm going to delete that in case I save the notebook, right? So the other thing that you can do, there's a zip function. So what the zip function does is essentially it transposes things, right? So If you say zip question and answers, then you'll get a list of tuples. The first item of the tuple comes from the first list, and the second item comes from the second list. If the two lists are of different lengths, then the zipped list is as long as the shorter of the two other lists. This is skipped. Right, so you'll see it processes all of the pairs that it can match up. Name to Lancelot, Quest and Holy Grail, and favorite color in blue. But then this list ended, and so zip finished generating pairs. Right? Again, what is zip question answers? What kind of a thing is that? In Python, a lot of these things that you iterate over are using delayed computation. They're using that yield function or something like it so that they don't even bother to generate a quantity which you're not planning to use. Right? Another useful trick for Python is when you're writing a range but you want to visit everything backwards, you can pass it to the function reversed. So here you go from 1 to 10 in steps of 2. So that's 1, 3, 5, 7, and 9. But you want to do it in reversed order. So you pass it to the reversed function. The neat thing about reversed is it is also using delayed computation. So it never generates the list or anything like that. It's just generating that sequence of numbers right when you want it. So it's a very clear way to indicate that you want to do it in reverse. I mean, compare that to range. I would have to start at 9. I would have to end at something below 1. And I would have to move in increments of -2. Right? So that I think that this is much clearer. If you want to remove the duplicates and process them in sorted order, you could do this. Now, unfortunately, making a set does jumble them up, but that's okay. We sorted it at the end. As a rule, you don't modify the sets while you're iterating over them in any language. You don't modify any collection while you're iterating over it. So if you find yourself wanting to do that, as we said, you make a copy, right? Here we have an example of an iteration technique. So we've got a list of values, which maybe it's the result of dividing by a number, and you've got a bunch of nans. So nan is what happens when you divide by 0, or you take the square root of a negative number. Actually, is that what happens? Python does have a complex type. But there we go. It does have a complex type, but it won't, for the square root function, it won't assume that you're using the complex type. You need to do something else. So I think I can say 1 to the 0.5 to get the square root. And if I say the square root of -1 like this, oh, remember what we talked about, the precedence rules, the order of operations? There we go. So Python does have a complex type. So by raising to a fractional power, I can see that the result is a complex type. However, the square root function, for instance, if I were to try to do a square root of 0, that is not the correct answer. Or is it? I guess that is the correct answer. How about this? If I were to take the log of 0, what do I get? There we go. Anyhow, very often, the point is very often you end up with these nans, right? Floating around and stuff. And you might want to get rid of them. So you go through each value in the raw data and you make sure that it's not nan. And if it isn't nan, then you can put it into your filtered list where you've removed the nans. I've had to do something like this a lot. Here's the same thing as a list comprehension, right? So it's just another example of a list comprehension where you can filter out the nans. So if we look a little bit more on conditionals as well, there's some neat stuff here. So if I set A equals to 3, B equals to 4, and C equals to 4, I can actually chain together conditionals like this. A is less than B, which is equal to C. What does that mean? It means A is less than B and B is equal to C. So when you start chaining things together, it's sort of like the items in the middle, you're inserting ands in between them like this. So A equals B and B equals C, and you can just more concisely write it like that, and Python knows what you mean. If I say 0 is less than B, 0 is less than A, and A is less than B, and B equals C, and C is less than 10, I can just write it concisely by chaining those operators like that. So that's a little thing. Another thing is that strings, for instance, can evaluate as true or false. So the empty string evaluates as false. The non-empty string evaluates as true. So it is going to return the true part. These ORs are short-circuiting, right? So if this is false, it returns the second thing. Banana, right? So if this one is false, it's going to return the second thing. And if this one is true, it's going to return it, right? So there we go. So that's kind of a neat thing that you can do. If the first thing is not empty, because empty is the same as false in Python, right? So here we generate 3 strings, but one of them is empty. And so we say the non-null string is string 1 or string 2 or string 3. And so it's going to evaluate whichever one of those two is not null first, that's going to be the one that it gets. So we expect it to get Trondheim, right? And also in Python 3.8, you can use the walrus operator, which is a colon equal sign. This isn't in Python 3.7. This is new to Python 3.8. You can assign to a variable inside of a conditional. So you can say, let x equals 3, and then check if the result is less than b. When I'm done, it'll say true, but it's also assigned the value 3 to x. So doing an assignment inside of an expression like this is now possible in Python, and that makes a lot, it's actually it's called syntactic sugar. So the term syntactic sugar in a language means a feature that's not necessary to allow you to do things, but it makes it possible to write programs. It makes writing programs a lot more pleasant, right? It makes it easier to do some things. On to section 5.8, we're looking at comparing sequences. So if I want to compare 2 sequences, it's always going to compare them in lexicographic order. Here we've got A, B, C. And that should be less than C because A is less than C. C is less than Pascal because C is less than P. Pascal is less than Python. The P's are both equal, so then you can compare the second letters, and A is less than Y. That's lexicographic order. In lexicographic order, the first time you have a character that's not equal, in this case 3 is less than 4, then you just compare those two, the first two that aren't equal to each other, right? Shorter strings precede longer strings, right? So here, 1 is equal to 1, 2 is equal to 2, and here, nothing is less than a -1. So the one on the left wins. So shorter strings win in lexicographic comparison. When we're comparing integers to float, it works if the values are the same, so the equal sign works. There's a caveat there, I'll show you in a second, and it's okay to use a mixture of data types. Let me show you the caveat. Is 1/3 equal to 3/9? I'm sorry. I'm going to keep doing this until I find one that is false. How can I do this? Okay, so this is the classic trick, right? So I take x and I set it equal to pi. Then I divide it by a really big number, and then I multiply it by a really big number, and they're not equal anymore, right? So if I want to print this, I print f. I can do x equals. I can do y equals, and I can do actually, I want to do this. And I can say this whole expression. Let's see how that works. There we go. So if I hit Shift Enter, so here x is pi, and y should be pi in theory. But if we look at them, 9, 7, 9, and instead of 9, 3, it's 9, 2, 7. So they disagree way out there in a few decimal places. So mathematically, these two should be equal, and yet they aren't equal. Right? So they should be equal, but they're not. And the reason is, and it can get even more confusing here, if I try to only print 0.4 decimal places, right? There we go. So x equals 3.142, y equals 3.142, but are they equal? No. And the reason that they aren't equal is because of floating point lack of precision. So you got to be careful when you're comparing up here floating point numbers. You should never be using the equal sign. You always want to be comparing whether their difference is less than a tolerance or something. My system is slowing down. I'm trying to drag this down to here. There you go. All right. So I added that. Okay, so another topic that I want to cover here is Python modules. So if you have a group of code that's supposed to work together, you can put it into a module. So again, returning to the Fibonacci sequence, we had two functions that computed the Fibonacci sequence. I'm using the Jupyter Magic %% file, which will write the contents of this cell to a file. And here we put the two functions fib of n and fib2 of n, one that prints the results and the other returns a list, into that file. Right? So I've generated the file fibo.py, and now I can import the file fibo. When I do that, it loads all of the code from that file into the fibo module. So the name of this function is now fibo.fib, and I can invoke it with 1,000, and it prints the Fibonacci sequence is less than 100, and I can invoke fibo2, and I get the result as a list. Right? That's with 100, by the way. Maybe I should make that 1,000. There we go. And I get the list. So that's nice. You can group things together into files. So generally, when I'm developing with Python, I'll often prototype an idea in a Jupyter notebook and do piece by piece build up the solution. And once I'm convinced I've got it right, then I'll put it into a file. You can open and edit Python files in the Jupyter notebook. So I can open fibo.py over here in a different file and make changes. However, it is not the best Python editor. If you're going to start editing the files, I recommend that you use PyCharm or Spider. Okay, but that's a Python module. You can access the fib function that's defined within it. So a little bit more on modules. You've seen me do this stuff. And hopefully we've glossed over it, but now we'll talk about it a little bit more. To import a module, you use the word import and the name of the module. Once you've imported it, all of the code gets loaded and executed. It all gets run at that time. After running all that code, you can access the variables that are global in that module, right? So for instance, fib and fib2 are functions. They're top level functions in that module. So I can access fibo.fib and fibo.fib2. Now, if I want to access, if I just want to pull those functions out of the module and bring them into my own namespace, then I say from fibo, and it'll run fibo exactly once. It won't run it twice. So you can't import the same module twice. It'll only actually do it once to run the code. Every other time you try to access it, it'll just read what the result was the first time it ran it. Okay, so from fibo, I'm going to import fib and fib2. So that gives me access to the functions fib and fib2, right? So I can just access them without saying fibo.fib. Now I can just say fib. I can still say fibo.fib too, but I've got a shorter name for it. If I want to get everything that came out of the module, I can say from fibo import star. And then, of course, I've got fib and I've got fib2. Also, I can import the module and I can give it a different name. So instead of importing fibo as fibo, I can import fibo as haha whatever, right? And then I can say haha.fib, right? So you can create an alias when you import the module. This is actually quite useful because some modules are so common you want to have a short name for them. For instance, import numpy is typically as np because you use the functions in numpy so often you want to be able to say something like np.transpose or similar, something similar to that, rather than saying the full function name, right? From fibo, you can import the function fib, and I can give it a name that is more appropriate in my context. For instance, I might already have a name, fib. So I want to call the function I imported from fibo something else, right? So from fibo, from the module, import the top level variable as and give it a name, right? And so that I can use it. Now, if you change the module while you're working on the notebook, so I might go back into the fibo module and make a change to it, like you saw I just had it open. In that case, I need to reload the module. And I think I might demo that later in this notebook, I don't recall. So here, I'm going to make a different version of fibo. So it's the same as the code was before, so it's going to save it to a file called fibomain.py. The only difference is I've added a line of code here. And the idea here is that this code right here will only execute if the name of this module is main. Now in Python, the dunder, this is called a dunder, the dunder name variable of a module gives you the name of the module. So if I were to check it out, I could say fibo.dundername, and it's going to tell me that the name of that module is fibo, because when I imported it, the module I imported was fibo, right? Even though I renamed it as haha, its name is still fibo according to the Python packaging system. So that's fine. If you import a module, then its name is set to the name of the module in the Python packaging system. However, when you're running a Python module, so every Python file is a Python module, at the top level, like when you're just running it from the interpreter, its name is set to main. So this was not imported, right? So if you were never imported, then your name is main. So here we're writing a piece of code that we're going to execute if this file is not imported, if it's just run right through the Python interpreter. Okay, so here we've created that module, and if you put a shebang, like a bang symbol at the front of the line, then it runs it through the operating system. So you can do like ls to list the contents of a file. I'm on Windows. You can do dir to list the contents of a file, for instance, right, on Windows. So that's kind of like, it just pipes it to the operating system. I don't want to do that. Here, we're going to go out to the operating system and say Python run fibomain.py, and we're passing an argument here. So when you pass an argument to a function, it ends up in the system package has an argument vector, and sys.argv0 is going to be fibomain.py, and sys.argv1 is going to be the first argument, and if I were to pass other arguments, then they would end up in this argv array. So when I run this, it's going to do all the Fibonacci numbers up to 50. Okay, so this is kind of how you write a command line tool. If I pop over into a shell, let me cd, where did I put this stuff? Oh, I put it right here. Is there a Fibo? Python fibo.py 50. Oh, no. Oh, I don't have Python. Okay, let me exit this bash. Okay, Python fibo main.py 50. There we go. So this is how you make your command line programs work. And just sanity check here. Yeah, so it doesn't know how to run it without saying Python first. There's a way to set your system up so that it does know how to execute them. But you say Python fibomain.py, and you can pass the arguments in, and you can write your own little command line tools that do all the automation tasks you need to do. Name is main. Run it 50. Okay, if I try to import it as a module, it doesn't execute that code because its name is not main anymore. It's the name of the module as it was declared to be. Okay, when you go to import a module and it tries to find those Python files, so out here you've got fibomain.py and fibo.py, where does it look? Where does it look to find those Python files? Well, it looks in this sequence of directories, starting from the beginning and working its way down. It stops the first time it finds a match. So these are all of the locations on my computer where it's going to look for a fibo.py when I say import fibo. So how does this path get set up? Well, before you run the Python interpreter, you can set an environment variable called Python path. And if you set that environment variable, then it'll look there to import a module, and if it doesn't find it there, it'll look through the whole sys.path stuff. Usually Python path isn't set, but you can set it. Hold on. I accidentally opened PyCharm earlier when I tried to run that Python script. Close. But you can set it to something. So for instance, if you were to say set, well, if I were just to say set, it shows me, no. Oh man, I don't know how to use PowerShell. I don't know how to use the command prompt. There we go, CLS. So if I were to say set here in the command prompt, you can see all of the environment variables. and there is no environment variable called Python path, but I could say set Python path equals to something. And I could set it to the folder where I'm putting my Python files before I run Python, and I should be good. The other thing that you can do is you can import sys, the system module, and you can actually insert the path where you're saving your Python modules into sys.path. So you can say sys.path.insert 0. The operating system module, OS, is a special module that has useful functions to manipulate your program's operating system. As a for instance, again, my computer is not happy. os.path.abs path will convert a relative path into the complete path that starts at c:\users\your name. So you can use that to get the absolute path of the file that you insert into the system. Now, people say that Python is an interpreted language because it is, but you'll also people talk about the notion of compiling Python files. And in this case, you need to be clear about what the context is. It is possible when you launch Python to pass in certain command line arguments, which some people say is compiling the program, but they aren't really compiled. They're just simplified a little bit. For instance, if you say Python-O and then you run a program, it'll remove all assertions. An assertion is an expression like this one, which will raise an exception if the condition is not true. So if something should be true, you can just assert that it's true, and you can even give a message to display when it's false. And when you're programming, it's a good idea to use a lot of assertions to make sure that while testing, the program runs as you expect it to. If you compile the code, quote, compile the code with the -O flag, it just removes all of the assertions. And if you compile it with the $OO flag, it'll even try to minify it further by getting rid of documentation and stuff like that. That's hardly compiling the code, right? So here, x is not less than 4, so this assertion failed. It throws an exception. Here's an example of a module. And in this module, if you invoke the function foo, it'll always assert false. It'll always fail, right? And if you get this far, then that means assertions must not be working, okay? So here I print 70 dashes, and then I display the help on the foo function, and then I display 70 dashes, and then I invoke the foo function. So here, if I run that file here, you'll see that it first displays help on the foo function, and then it failed due to an assertion error. Now, if I run Python-OO with all of those optimizations, when I try to print the help on the function, it prints nothing because OO removed all the help. Also, I was able to execute this code that printed that line of code, which means that it did not check this assertion. So that's kind of what the O and the -OO functions do. A little bit more. So there's some standard modules that you should know how to use. There's a bunch of them. I've spent way too long already, but one important Python module to understand is the sys module. Both sys and OS have information about your system. OS is more about your operating system, whereas sys is kind of about your Python system itself, right? So sys.path is the search path for modules. Sys.maxSize is the size of it's the maximum value that you can use to represent the size of an object in memory. So Python is able to represent integers that are much bigger than this because it'll automatically convert to big integers, right? So I could say x equals sys.maxSize times 100, and that's fine. X is just stored in a different data type than an integer. It's got a big int, right? So if I say type X, it'll turn into, well, I guess it's still an int. How about times something that's way bigger than an int, times 1e20, right? Oh, I turned it into a float. Maybe I was a little bit, I went a little bit overboard there. I might have killed it. Okay, so the idea is that as numbers get too big to represent as integers in Python, it's supposed to automatically switch into a big int type. But I might have gotten a little bit too much bigger than an integer there, and killed the system. Maybe even that would have been good. Anyhow, let me just restart the shell. Restart. Let's try this one. Import sys.path, sys.maxSize, sys.maxSize square. The type of x is still an integer. I thought that the data type would actually change to be something other than an integer and to being something called a big integer. Anyhow, that many digits is well beyond what you should be able to actually store in an integer. So Python will actually keep enlarging the size of the integer. So right now it's 441 bits, where an integer really should only be 32 bits long. And long, you know, so 32, maybe 64. We're already at 441 bits. So Python will dynamically enlarge the size of an integer to fit whatever number is needed. In the sys module, you have a standard error stream. It's a file, and when you write to the file, it gets displayed as an error message. You can access in sys.executable, it's the Python executable you're running. And here you can see the executable is called Python, but it's not the default Python, it's the one inside of a folder called CSE465, inside of a list of environments that I've created using Anaconda, which is stored here on the computer. If I want to get the folder that contains my Python exe, that's what it is. So if I wanted to store something alongside it for some reason, I don't know. If I want to get the version of Python I'm using, you've seen me use that in the very first cell of this notebook. If I want to figure out whether I'm running on Windows or OS X, I can use sys.platform. So Win32 is most Windows systems. Sys.argv. So when this Jupyter notebook was launched, I used the IPyKernel launcher with the flag -f and then this big JSON file. So I didn't do it, the web server did that. If I want to get information about the floating point data type, I can access the maximum float that I can represent, the largest exponent. The largest exponent base 10 is 308. You can see it over here. The minimum is -308. The min exponent, -1021. So you get all of these different things. Epsilon. When we talked about rounding errors, when a number gets smaller than epsilon, then 1 plus epsilon yeah. So it can't tell if you use any number less than epsilon, it can't find it. At least at 1. So 1 plus epsilon is equal to 1. 1 minus epsilon Yeah, so 1 minus epsilon over anything smaller than that it's gone. Let's see, maybe the plus is better. Now it matters about the size of the thing, so that didn't work. Oh, that's why, because I made it bigger, 1.1. There we go. Any, the way that it's supposed to work is that any number plus epsilon is equal to that number again, right? So in this case, I had to divide it by 2. I don't know why. But that's the degree of precision of a floating point number at 1. As the numbers get bigger, then epsilon gets bigger as well. As the number gets smaller, then epsilon it changes. So it has to do with the exponent. The dir function is also useful. So you can import multiple modules on one line like this, but I never do that. If you use the dir function, it lists all of the top level variables of that module. The variables that begin with a double underscore are special variables to Python. These ones are the ones that are so double underscore is kind of private. You're not supposed to access it. Fib and fib2 are ones that are actually accessible to me. If I want to get all of the names that are not with the underscores, I can use this little list comprehension where I go through each name in the directory of Phoebo if the first 2 characters are not a double underscore. All right, I can get those things. In addition, if I use dir with no arguments, it gives me all the variables in my current module, and there's a lot of them, so I'm just printing the first 10. So this is the cells that would be executed. Listed in alphabetical order, right? So these aren't the first 10 that were actually executed. If I import built-ins, these are all of the different variables, special words, right, that I don't have to import. So the built-in modules has all of the names in Python that are, there's all of the symbols in Python that are not reserved words, but that are available without importing them, like the type bool, the function breakpoint, isInstance, int, input. So I guess it even has some of the reserved words. Interesting. So another thing about packages is sometimes you have a bunch of different modules that are related to each other and you want to lump them together in multiple files, in which case you have a top level package, for instance, and perhaps sound is a top level package. When you import sound, it'll execute the file called dunder.init.py, which is py in that folder. So instead of having a sound.py file, you could have a sound folder, and then inside of it, a dunder.init.py file. And this is the code that will execute when you import sound. And then nested under that, you can have this one, which would be called sound.formats, and it has its own init.py. And then here, this would be called sound.formats.waveread, right? So you kind of have this hierarchical structure where init.pys are sort of the default files of a folder, right? So here we're going to execute some cells using the bash prompt. So in the Jupyter Magic, I say I'm going to use bash. I'm going to use the make directory folder, and -p means it's okay if the folder already exists. So this is permissive. It's going to make a folder called foo, and then inside of foo, it's going to make a folder called bar. And then I'm going to create the empty file init.py. So touch will create a file if it doesn't exist. If it does exist, it'll change its modification time. And then I'll make an init.py in foobar. And then I'm going to put the string print you imported me into the file foo/bar/buzz.py. And then I'm going to append to that the function fizz, which is supposed to print the word pop into foo/bar/buzz.py. So when I'm done, if I input foo.bar.buzz, At the moment that I imported that module, it displayed you imported me. All right, so the full name is foo.bar.buzz. Okay. Again, from foo.bar, I can import buzz. It did not say that you imported me because it only ever executes the code associated with that file once. If I want to execute it again, I have to import the importlib module and say importlib.reload buzz, and then it says you imported. So then it re-executes this code that says you imported me. From foo.bar.buzz, I can import this function. So just that name, I'm importing it, and now I've got access to the name fizz. If I look at that function, its name is foo.bar.buzz.fizz. Okay, so but I've got, shorter access to it. Occasionally, you want to import everything from a package. So in that case, you can say import star. For instance, from math, we might want to import everything so that I can say the cosine of 30 or pi without having to type in math.pi first. So the other option is to say math.pi, and that is, math.pi for the constant pi, not pi is in Python, if I were to import math. All right, this is a lot more to type, and it's very cumbersome because if you're going to use a cosine, you're probably going to use a sine and an arctangent and a tangent and pi, and just saying math everywhere is really ugly and tedious and error prone. The problem is if a module imports pi, and then you import, if the module imports star, and then I import star from that module, before long I've got a lot of names. If you want to, you can limit the number of names that you import by defining a dunder all variable. So if you were to add dunder all equals fizz, then the only names that you would import when you imported star would be fizz. The other thing that you can do is instead of defining an all variable, you can just import and give it a short name. I do that very often because I think it's easier to navigate a hierarchical set of names. But instead of typing so much, I'll give it a short name. So numpy is np. And by the way, that's not me. That is the convention of Python, right? Numpy is called np. And a lot of these modules, the creators give them short names that people will tend to prefer to use. PyTorch.nn.functional is F. That's used in deep learning. Albumentations is also used in deep learning. I don't know what the convention is. I just call it A. Matplotlib.pylab has a module called plot, or PLT, and then I'll just import that from the whole thing. Because it has all of the functions you need to do plotting and visualization, which is nice. Takitem is a progress bar library. It only saves me 2 letters, but the issue is inside Takitem there's a function called Takitem. So in order to keep it straight, I'll rename the module as TQ. So that's kind of how I deal with things. When you're trying to make cross references between packages, this doesn't work from a script. So I can't write a package name relative to the Jupyter Notebook or relative to a Python file I'm running as a script. But if I'm importing the package as a module, and that's the only way I intend for it to be used, then I can use a relative import. So from dot, that is the module that contains this one. So in this case, it would be like a bar, right? So from buzz, dot would be the bar folder, right? So from the same level I am in the folder, I could import echo. From one level up, I could import formats. And from one level up and then down into another parallel module called filters, I can import the equalizer module. So you can kind of use dot to find things that are your siblings in the hierarchy, and double dot to find things that are your relative to your parent in the hierarchy, or at your parent's level of the hierarchy. So there is, I'm not going to cover this thing. And input and output we'll have to rate for another time. We already talked about the print method and the input method. I think that's really all I need to say right now. There's a lot you could dive into. We've barely scratched the surface. We didn't even talk about classes in Python. So I think maybe in another video I'll address the use of classes. But if you're not doing any classes or object-oriented programming yet, this is a super duper detailed dive through the tutorial. My voice is sore from talking so much. I hope that this is useful. I don't know if I'll have time to go back and bookmark this, but it might be worth the time to do so. I'm signing out. When I get a chance, I'll upload this notebook so that you can play with the things that are in it. And that will conclude this stream.